This comprehensive Python data science course covers the essentials through theory, demos, and real-world applications. With 2 detailed projects, this course is designed to provide practical experience that will prepare you for real-world data science. You'll gain hands-on knowledge in data analytics, A/B testing, and business intelligence.
If you are an aspiring data analyst, data scientist, or you are aspiring to get into the field of machine learning or AI, then mastering the basics of data and analytics is your starting point. In this comprehensive 6+ hour course, we are going to start with the Python implementation of data analytics. We are going to look into the data analytics basics when it comes to putting that in Python programming. After this, we are going to get into the A/B testing theory, which is fundamental for any data analyst or data scientist who wants to drive the experimentation changes in the product like UX design to the algorithms using the data. This course will consist of 3 parts. The first part will be dedicated to the Python data analytics course. In this Python data analytics course, we are going to cover the basics of performing a data analytics, including data visualization and data preprocessing in Python. After this, we are going to get into the second part of the course, which consists of the theory of data analytics and data-driven experimentation. This is fundamental for any data analytics and data science professional. Here you are going to learn the A/B testing theory, starting from the hypothesis, the business problem, up to the point of conducting a data analysis on that collected data to make a data-driven decision for different sorts of online problems. Then we are going to get into the third part of the course. In this third part of the course, we are going to conduct the 2 end-to-end portfolio projects. The first one will be related to the A/B testing, where we will conduct an end-to-end A/B testing online analytics-related project, which you can also put on your resume. And in this 1/2 hour, we are going to cover from the basics of A/B testing results analysis in Python to the actual implementation of it and conducting your data analytics in Python programming. And finally, the third part of the course will consist of 2 separate end-to-end full data analytics projects. The first one will be about online testing, where we will use the data analytics as well as Python programming to derive the landing page UX design decision on the landing page of LunarTech.ai. And then the second portfolio project will be another 1/2 hour end-to-end data analytics project, where we are going to look into the data analytics for a Superstore project. So those 2 projects, in total of 3 hours, will be a great way to implement the theory into practice in an actual business, real-life setting. Tatev and Vahe, data scientist and AI professional, and I've been in this field for more than 5 years. I'm co-founder of LunarTech, where we are making data science and AI accessible to everyone, individuals, businesses, and institutions. So here is what we are going to cover as part of this full data analytics course. In the first part of the course, we are going to cover the data analytics in Python programming. So it is expected for you to know some basics in Python, but not more. We are going to learn how to load data in Python using pandas, how to do data wrangling and data preprocessing using libraries such as NumPy and dpandas. Then we are going to look into the data preprocessing techniques, how to do sorting, filtering, as well as data aggregation, how to join data using different joins, including inner join, left anti-join, right join, how to do different statistics-related tasks, including calculation of data, descriptive statistics for our data using Python. Then we are going to do data sampling in Python. We are going to learn different data sampling techniques. And we are also going to look into data visualization in Python, which is really important as a data analytics professional when it comes to bringing the theory of data analytics into practice. So after this, once we are done with the practical programming section for the data analytics in Python, we're going to get into the second part of this course, which is about A/B testing. Here we are going to look into a quick high-level theory behind A/B testing, and then we are going to dive deep into it. we are going to learn this idea of A/B testing, online experimentation, and how the data analytics is relevant for A/B testing. And we are going to learn this entire cycle of A/B testing, from the design up to the data analytics of the final results. Be prepared to learn here the concepts like primary metric, the design of the test, how you can design a proper A/B test, including choosing the right parameters for your test, calculation of the minimum sample size. So as a prerequisite for this part of the course, it requires for you to know some fundamentals in statistics. So understanding this basics behind probability theory, this concept behind normal distribution, how you can use a sample to derive insights about your entire population. And once we are done with this theory behind A/B testing, and we have also learned how you can conduct the data analytics and final data analysis for your A/B tests, we are ready to go into the third and final part for our data analytics full course. In this third part of the course, we are going to conduct 2 end-to-end case studies. In the first one, we are going to conduct a data-driven decision-making for LunarTech's landing page, where we are going to use data analytics, data visualization, as well as A/B testing to understand whether we need to replace our current button. So here, expect to use Python. In this 1.5 hour course, we are going to conduct data wrangling, data preprocessing, also data visualization, and then we are going to analyze our results and make a decision by using the theory that we learned as part of the second part of the course, as well as the programming that we learned as part of the first part of this course. Then, once we are done with this first end-to-end portfolio project, we are then ready to go on to the second project as part of this final part of the course, which will be about a pure data analytics case study. In this case study, we are going to conduct the data analytics for our Superstore. So here we are going to start with the overview of this analysis, and then we are going to analyze Superstore customers. Then we are going to see what techniques we can use and how we can conduct a Superstore customer segmentation analysis in Python. Then we are going to analyze the revenue of the Superstore by customer segment. After this, we are going to explore the customer loyalty at the Superstore. And then we are going to finish off with the insights that we derived based on this analysis for our customers from the sales and just in general. So we are going to analyze the sales of these customers by segment, and then we are going to conclude. At the end of this course, expect to learn all the essentials for your data analytics journey. So without further ado, let's get started. Hi there, and welcome back. In this demo, we are going to talk about how to load data and view this data in order to obtain more information about a certain data that is provided to us. We're going to learn how to load CSV files, how to load TXT files, how to load Excel files, as well as JSON files, and also how to load SQL database. For this one, we are going to use predominantly the pandas library, a library that we spoke about in the previous demo, but we are also going to use some other libraries. All right, so without further ado, let's actually go ahead and learn how to load CSV files in Python. So for that, the first thing that I'm going to do is to import the pandas library. Import pandas as PD. And then the next thing that I'm going to do is to pick the name of the CSV file. So you might notice that in the left-hand side in our PyCharm, you can see that we have a file called %bachelor's_woman_USA.csv. This is a CSV file containing the following data. So you can see we have information about the year, agriculture, architecture, art and performance, etc. So you might have already guessed that we are dealing with the data that describes the percentage of the females that have completed a bachelor degree in the corresponding fields and the corresponding year of it. Well, let's go ahead and load the data in the Python. For that, what I'm going to do is to use this pandas library. And as an acronym, we usually always write a name of PD for the pandas. So let's go ahead and name our data frame, which we will call, let's say, data_CSV. And this will be equal to, and here we need to take the name of the library we are going to use, which is PD. which stands for pandas, dot, and then read underscore. As you can see, we are getting already many options. So we have read underscore CSV, then we have read underscore Excel, we have read underscore HTML, JSON, Parquet, Pickle, SAS. So here you can see all sorts of data formats that you can, file formats that you can import. And we are going to learn a few of them. And those are the most popular file formats that you can expect whenever you are entering the data science field. So as we have a CSV file, we are going to use the read underscore CSV option. And within the parentheses, we always need to specify the name of the file we are dealing with. So you always need to put the name of the file as it's a string, so within the quotation mark in here. So let's go ahead and actually print our data frame to see what is actually going on. Here we go. So you can see we are getting our data nicely. So we see that the headers is recognized. So we see the column names. We see also here the indices corresponding to our observations. And this is really a great way to look into your data for the first time. In the same way, by using exactly the same function, so read underscore CSV, we can also load a TXT file. So TXT and CSV files are pretty similar to each other. So in case of CSV files, which stands for comma-separated values, we do not usually specify that the separator is comma. So as you can see in here, this is a CSV file, and the values corresponding to each of the columns are separated by a comma. And if we're dealing with a TXT file, in the TXT file, we don't really know what the separator can be. Sometimes it's the comma, sometimes it's the space, sometimes it can be entirely different character. So it's really up to the data that is provided to you. But one simple way to load a TXT file by using exactly the same function, so the read underscore CSV, is the following. So here we have two different TXT files in here. We have the student grades.txt and the student schools.txt. Go ahead and use them. So we have data underscore txt, and it's equal to pd.read underscore txt. And then here within the parentheses, we have, let's say, student and then schools.txt. So this is the path. But before moving on towards the other arguments, let's actually go ahead and click on this to see how it looks like. So you can see we are dealing with a TXT file where we do have the header. So we have the name, school ID, and country, which all represent the name of the corresponding columns. As you can see here, we have the name, here we have the school IDs, and here we have the countries. And another thing that we can notice is that we are dealing with a separator in the form of commas. So therefore, what we need to do is to provide in here, by the way, instead of TXT, we will just use CSV for simplicity. And here, we will mention that the header is equal to 0. So the first row corresponds to the header, which means that that row should not be counted as the data. And then the next argument that we will use, just for knowing how to use it, is the separator. So here we will mention that the separator being used to separate each column's value in the row is the comma. But if you were to be supplied with the data in a more difficult format where you had a different separator, so let's say the separator is percent symbol, then here you need to specify that your separator is this symbol. So whatever the symbol is used, the character is used to separate your data, that's exactly what you need to put in here, such that Python can understand when it needs to cut and needs to take that value and say that this value corresponds to that specific column. And then the same holds also for the header. If your header is not present, then you need to specify that in your argument header. All right, so let's go ahead and load this data and see what is underneath. So print data underscore txt. Here we go. So as you can see, we nicely get all 7 rows. So the first name is Tina, the last name is Anna, and then the country, Canada, and the last one, Armenia. So let's go ahead and check it in here. So I always recommend to check the first and the last rows of the database to make sure that you correctly have loaded your data and you are not missing any information from your database. The next thing we are going to learn, and you have a name of your first sheet equal to sheet 1, and then the second one corresponding to another name, and you have multiple of those pages in your Excel file, is how to load Excel files. So let's say you have an Excel file and you want to load only the first page. Well, for that, what you can do, in here, I'm not going to look into a specific Excel file. Feel free to search for an Excel file or maybe one that you can create yourself, and then create your own pages within your Excel file and try to load that in Python. But for now, let's assume that we do have that Excel file in our PyCharm environment, and we are going to load that. So data underscore Excel will be the name of the data frame that we will store our data. And then the function we can use is pd dot, and then read. And then here we already get a recommendation from PyCharm, read underscore Excel. And then here we have file underscore XL. SX, which is a common extension of the Excel file. File.xlsx is the name of your Excel file. And here I'm making an assumption that your Excel file is within this Python for data science or your own folder, the one that you are currently using in PyCharm. So here then the next thing we need to specify is the exact spreadsheet we are looking into, because otherwise you will get an error in a PyCharm, and PyCharm will not recognize where exactly it needs to look for the data. Therefore, we need to use this argument called sheet underscore name, and here you need to specify the name of your exact spreadsheet you are looking for. It can be that it is the default acronym usually used in Excel, but in case you have renamed it or someone has renamed it, then you need to specify that specific name. So it can be, for instance, first spreadsheet, let's say, if that's the name of your first spreadsheet, or it can be sheet 1, which is usually the common convention used in Excel whenever you are not changing the name of your spreadsheet. And this is how you can read an Excel file. I won't be running this code because we do not have the file .xlsx in our folder. But this is something that you can experiment yourself. And another common file format that you can expect is the JSON format. Here, once again, we are following the same idea as in case of Excel files. So feel free to go ahead and look for JSON file online, download it, and try to load that into your PyCharm environment. But this is the way that you can load JSON type of data. So data underscore JSON is equal to pd.read underscore JSON, and then here you can specify the let's say JSON file.json. So this will be the name of your file. We can also make this more convenient. So let's make it file name. Here also file underscore name, and this is the only thing that you need to specify. So this will be the name of your file. And here, once again, I'm assuming that your file underscore name.json is actually in this folder that you are currently running. Otherwise, you need to specify the exact path of the file that you have. So once you write this, then you should be able to successfully load your JSON type of data in your PyCharm. And then finally, we will look into a way to load SQL databases. So SQL databases are common database format whenever you are working with big data. This is very common in the field of data analytics, but I think it's still worth to know at least the commands and the library you can use in Python in order to load this type of data. So let's actually go ahead and import the corresponding library we can use to load SQL database. And the library is called SQL TE3. So for that, we will do import and then SQL and then ITE and then tree. Then what we need to do first is to make a connection with the SQL database. And that's exactly what we can do by using this library. So connection db is equal to SQL ITE tree dot connect. And here we need to specify the name of the database we are dealing with. So database underscore name dot, the extension is DB for database. And in this way, you will make a connection with the corresponding database. The way SQL works is that in SQL, we are creating databases, and within each database, we can have multiple tables, and each table has its own name. And then within each table, when we are loading that table, we can then run queries. I won't go too much into details about what is SQL, how you can use database, how you can create tables, and how you can run queries, because that's outside of the scope of this course. But I would highly suggest you to at least learn the basics of the SQL. It's not necessary to enter the field, therefore it's also not included as part of this course, but it's good to know at least what SQL is, and also how you can use it, and what is the functionality of SQL in the entire world of data science. So I will include some resources about SQL and the usage of it in the resources section. But just know that in order to be a technical data scientist, at least to enter the field of data science, you do not need to know SQL. It's something that I would highly suggest you to learn as you grow in your career, but it's not a must-know. So once we have made the connection with our database called database underscore name.db, then we can specify the exact query that we want to run. And in this specific scenario, what we mean by the query is that we will use the commands commonly used in SQL in order to select all the rows within a specific table. So in our database, we can have multiple tables. And here I will assume that we have a specific table from which we want to import, let's say, the first column only. For that, what we need to do is to do a query. Let's call it a query. Let's say it's our first query underscore 1 is equal to, and then here we have quotation mark, and then select. This is a common way of specifying that we want to select specific variables from our table. And here we can specify the name of the column that we want to import. Let's say call underscore 1. And then we need to specify from. And here we will specify the table underscore name. And in this way, the query 1 will then go ahead and select the first column from the table with the table underscore name. So this is one way of running a query and selecting just one variable. We could also write a query, we will call it query 2, and this will select all variables from table underscore name. Select. And then here, what we need to do is use star. And in SQL, whenever we are saying select star, it will go ahead and select all the columns included in that data, something that we usually prefer instead of just selecting one variable. So you will select certain variables only if you are specifically looking for those features. But otherwise, I would highly suggest you to include all the columns. All right. By the name of the data frame we want to load this data in, and then we read underscore. As you can see, we already see something. So here you can see that we have 3 different functions we can use. We can use read underscore SQL, we can use read underscore SQL underscore query, or we can use a read underscore SQL underscore table. They do differ in the way they import the data. So for one, for instance, you can specify also the schema, and another one you can specify the index of the column you want to import. The most generic one is the read underscore SQL, similar to the read underscore CSV. So we are going to use that one. And the next thing we need to specify is the query and the connection. Is to specify query underscore 2. And then next thing I need to do is to specify the connection. So once you run this code, what this will do is to make a connection with your SQL database. It will then specify the query, and it will go ahead and select all the features and import all the features from a table called table underscore name, all the variables, and it will then be stored in the pandas data frame. This is all for this demo, and I will see you in the next one. In this demo, we are going to continue the process of looking into the data. As in the previous demo, we'll learn how to load different sources of data. And in this one, we are going to look into it. We're going to learn how to explore the data and how to preprocess it. we're going to discuss the inspection of the data, getting information about it, getting to know what the shape of the data is, how to identify missing values, how to drop the missing values, how to fill in missing values, how to get the type of the data you're dealing with, how to access different rows in your data frame by using the infamous ilog and log, and what is the difference between the two. So from the previous demo, we still have the CSV file, and we saw that we got this data structure in the CSV file describing the percentage of the bachelor degrees consisting of women in the USA. So this is how the data look like. We had the year, agriculture, architecture, art and performance, etc. And then in total, we got 18 columns in this data frame and 42 rows. So the rows are those observations. So you can see in here. And the columns are all the features included in the data frame. And we got only one feature describing the year, and the rest of them are all the names of different sorts of bachelor studies. So as you can see, we have agriculture, architecture, we have social sciences and history, public administration, etc. The first thing we are going to look into how to use the header functionality in Python in order to get a snapshot of the data. So what we can do here is to write down the name of the data frame, so data.csv. And what we need to do is to do dot and then head for the header. And then here inside in it, we can leave it empty. So when we do that, what we will get is the following output. So let's actually go ahead and remove that one from the printing temporarily. As you can see, it will print for you the first 5 rows, but all the columns. And if we specifically are looking for X number of rows to be presented as part of the snapshot, then we can specify that as part of the head function. So in here, for instance, we can say show to us the first 100 observations in this data frame. And in that case, it will print for you the first 100 observations. But as we have only 42 rows, it means that it would need to print for you all the rows. If we change this to 20, let's say, then in that case, we will get the top 20 observations present in the data. And this is how it looks like. All right, so this is about header function, just a good way to have a first look at what kind of variables you have, what are the first 2 columns, what are the last 2 columns, what is the number of observations you got by looking in here, what is the number of columns you got, and also what are the different sorts of variables you got and the data types in your data frame. Just by visual inspection, you can see that we have, for instance, the year column, which consists of the integers. We have the agriculture, architecture, and all these other variables that are of a floating number type, which means that we got a number and then we got dot, and then what comes after the decimal points. And if this header function will print for you the top X observations, we can do exactly the same only from the bottom observations. And for that, we can use a function called tail. So we can print, for instance, the last 20 columns by using this data underscore CSV dot tail, and then within the parentheses, the amount of rows that we want to see from the bottom up. So let's go ahead and print that. And as you can see, if the header function will showcase the first 20 rows, the tail function will showcase the last 20 rows. So you can see 22, 23, up to 41. So this is a great way to see how the first few rows look like and how the last few rows look like. The next thing what we can do is to use this info function in order to obtain more information about our columns, so their data type specifically. So this is the output of the info function, and this is the number of columns you have. In this case, the year is the first column, the agriculture is the second column, and then the social sciences and history is the last column. And then we have the count of the non-null values. As you can see, all the columns have 42 non-null values, which means that we do not have any missing observations. Then we have the data type corresponding to that specific feature. And we already saw from the snapshot that the year was the only variable of integer type, and everything else was floating data type. And this is exactly the confirmation for data observation. The next thing what we can do is to identify the missing values and drop the missing values. So from this, we can already see that we do not have any missing values, but let's actually go ahead and learn how we can do that. So let's say we want to drop all the missing observations. For that, what we can do is to do print, is to actually take the name of the data frame, CSV, and then what we can do is to do drop, and then NA, and then parentheses. So in this way, you will be dropping all the NAs, so all the cases where your observation has an NA for that specific column. So as we do not have any missing values in our data frame, this will not do much to our case. But I think it's really important to know how to drop missing values in case you want to quickly remove them from your database. Let's say you do not want to drop your NAs, so the missing values in the form of NA, but you want to fill them with a certain value. What you can do is to use this fill NA function, and within the parentheses, you just need to specify what is the value that you want to use to fill the NAs. So in here, you can, for instance, decide to put null instead of NA, and this will simply go ahead and fill all the values where it's written NA. It will replace it with null values. So let's say you have another issue with your data. So you have rows that are exact copies of each other. One function you can use is what we call drop duplicates. So for that, you simply need to take the data frame's name, and you need to do drop and then underscore duplicates, and this will quickly remove all the duplicates from your data frame. So let's actually go ahead and change the CSV file and see whether we can nicely remove the duplicates. So let me copy paste this a few times. And as you can see, it's the exact copy of the third row. And now we have it in the fourth and fifth and sixth rows. So let's go ahead and check whether this drop underscore duplicates really removes those duplicates. So let's print the actual CSV file before removing the duplicates and after removing the duplicates. In here, let's see. So in here, you can see that this is the data frame with in total of 45 rows because we just added 3 additional rows. So previously we had 42, we added 3, so we end up with 45 rows, and the number of columns is the same. And then we apply the drop duplicates function. And as you can see, after using that function, now we once again end up with the 42 rows. And if we go ahead and look into the specific column we duplicated, you can see that we got only 1 row corresponding to this year. And this is how we know for sure that drop underscore duplicates really works, and it will remove the duplicates from your data. The last thing we will look into in this demo is how to access certain rows in a data frame depending on their index type. So sometime, and actually most of the time, we will get a data frame that has an integer as an index. And that's also what we got in our data frame. As you can see, the index is 0, 1, 2, 3, 4. So it's in the integer format. But there are also occasions when you will get your data frame with an index that is of string type. So you will see that instead of the index 0, 1, 2, 3, for instance, you will have A, B, C, or A1, A2, A3, etc. So depending on this nature of the index that you are dealing with, you can then use either the ilog or the log functionalities in Python in order to access different rows in the pandas data frame. And this is, by the way, a common question you can expect during your programming-related data science interviews. What is the difference between the ilog and log, and how you can use them? So let's start with the ilog, as our data frame already contains an integer-based indices. And let's say we want to access the data in the index 10. So this is the row that we want to access. Therefore, what we need to do is to take the name of the data frame, so data underscore CSV, and then we need to do dot and then ilog. And then in here, we need to specify the row that we want to access, which is a 10. And let's go ahead and print this to see whether we are getting the correct data. And let's verify that by looking at the year. So as you can see, the year is in incremental order, and we do not have duplicates in the year. So therefore, if we see that the year is equal to 1980, then we have selected the right data and we have accessed the right row. So this is the output. And as you can see, the year is equal to 1980. And this is all the information that is stored in the 10th row. And in this way, you can access any row that you want in your data frame. So it can be, for instance, the first row or the last row, but it can also be a row somewhere in the middle that you want for some reason. And if you want to access a specific column instead of specific row, what you can do is to use, again, the log function. So data.log. And here, instead of providing just one argument, you can then provide two arguments. So we always have the rows in the beginning, and then we need to specify the columns. And in case of what we did was to access the specific row. Therefore, we specified only the X. But if we want to access a specific column, we also want to specify the rows that we want to include. Then we need to specify both the index of the rows and the index of the column. So let's say I want to access the column A2. In here, I will then specify A2. And as I've specified here a column, this means that I want to take all the rows, so the indices corresponding to all these values. So let's see what the output of this one is. And as you can see, here we are getting 4, 5, and 6. So the value corresponding to the index X, Y, and Z. And this is actually the column A2. So in this way, you can specify not only the rows that you want to access, but also the column. So let's say you only want to access a specific value in that column. Let's say you want to access the second row and the second column. In that case, what you need to do, I'm sure you already have guessed it, is to specify the index of the row and the index of the column that you want to access. So the index of the row is Y, and then the column that we want to access is A2. So this is the number that I'm chasing. Let's see whether this will provide the value. And as you can see, it provides 5. And let's also look into the case when we are dealing with a string-based index. So let's create for that a small data frame, and it is the following. Let's look into it. And as you can see, this is the small data frame that has indices X, Y, and Z. And let's say we want to access the data that is stored under the index X, so very first row. Well, what we need to do for that is to, once again, take the name of the data frame. And instead of using ilog, this time we need to use the log, and then the index name, which is similar to what we saw before. So the index name is X, that's what we want to access. And let's actually see what is the output of that. Print. Here we go. So as you can see, the first value is 1, the second value is 4, and the last value is 7. So by using the log functionality, we can access the row in a data frame where the index is of string type. But if you go ahead and you use the ilog in here, you will see that you will get an error. And the reason for that is because ilog doesn't allow you to search with a case when your index is of string type. And for those cases, you always need to use the log function instead of ilog. Hi there, and welcome back to another demo. We are going to talk about 3 very important tasks that you can perform as part of your data analysis and data manipulation toolkit. So we are going to learn how to do filtering, sorting, and grouping in Python. Data analysis and manipulation involve working with large amounts of data, and you can definitely expect this as part of your data science project. And then what you need to do is to extract meaningful insights. In this context, filtering, grouping, and sorting are really important techniques that allow us to organize, extract, and analyze data efficiently. Python has a very powerful tool, library called pandas that we also saw as part of the libraries discussion demo, which can be used in order to perform grouping, filtering, and sorting in a very simple way. So when it comes to grouping data helps us to analyze and summarize information and data based on specific criteria. Here we need to have at least one variable to do the grouping based on, but then you can also add extra other variables such that you can aggregate your data not only on one variable, but on multiple variables. So let's say you want to group your data based on the gender or based on the region, and then you want to perform some descriptive statistics calculation. So you can calculate the mean, for instance, the standard deviation, the variance, the median, the mode, the minimum, the maximum. You get the idea. So you can then categorize your data into certain groups. And this way you can group your data and then you can obtain some meaningful information and analyze your data. This is usually a very important part of your data preparation process. Another thing we are going to talk about is how to filter the data. So whenever you are filtering your data, it helps you to extract subsets of data based on specific condition. So let's say you know a specific year that you are interested in, or you are interested in a specific region, you are interested in a specific characteristics, then you can use filtering to filter your data, to select only a subset of observations from your data, and to perform all the analysis, calculation, and training of your model based on this specific subset. Or it can also be that you want to identify the outliers in your data or the noise in your data, and you want to identify the 99th percentile or the first percentile, so you want to identify the largest or the smallest observation in your data and remove them from your data such that you won't be dealing with the problem of overfitting, as an example. Another thing that we are going to learn as part of this demo is sorting. So sorting data helps you organize information in specific order. It can be in an ascending order or in a descending order. It can help you to visualize your data. It can help you to identify certain patterns, find extremes or outliers in your data. And sometimes it's also used as part of the time series analysis, or for instance, to look into the sales performance, to identify the worst performing shops or the best performing shops. And it's essential part of the re-ranking and recommender systems. So whenever you are dealing with search engines, recommender systems, anything that relates to the order and importance, then sorting data comes really handy because you want to show the best information, the most important information to your customers. And the way that you can do that is by sorting your data. So when it comes to the ascending versus descending, the ascending relates to the case when the smallest values are at the top, and then the values would then increase, and then at the bottom you have the largest observations. And whenever it comes to the descending order of the sorting, then we have the largest values at the top, and then the values would decrease, and then the smallest values will be at the bottom. So here I've created a very simple data frame using Pandas library. And here we have 4 different columns. We have the name, the age, the salary, and the department of an employee. And as you can see, we are dealing with 8 observations. The name and the department are of string type, and the age and the salary are of integer type. And what we want to do here is to sort our data under the data frame name data with respect to the salary, such that in the beginning we have at the top we have employees with the smallest salary, and at the bottom we have employees with the largest salary. So what we expect is that this person, so this corresponds to Sana. Sana at the age of 19 from the Department of Operations should be at the top because this person earns the least. And then we have the largest earning, so the highest earning person, which is named Bob. And Bob, with the age of 20, should be at the very bottom because we want first to sort our data based on salary in an ascending order. So for this, what we can use is the default pandas function called sort_values. So data.sort_values. So as you can see, we are already getting a recommendation for this function from Python. And here you need to specify based on which variable you are sorting. And then you need to specify whether it's an ascending or descending. So the reason why we need to specify the variable's name based on which we are sorting is because here we could have also sorted the data based on the age. But instead, what we want to do is to sort the data based on salary, such that the highest earners will be at the bottom and the lowest earners will be at the top. Therefore, we need to specify that by is equal to salary. And then when it comes to the other parameter or the argument in this function, which is ascending, this is a Boolean type of argument. So when ascending is equal to true, which is the default value, then it means that we are sorting our data frame based on an ascending order. But if we want our data to be sorted in a descending order, then what we need to do is to change this value. So then the ascending argument should be equal to false. So let's actually go ahead and see that in the implementation. So here we need to specify by is equal to, and then the name of the variable based on which we are sorting, which is the salary. Then the next thing what we need to do is to mention ascending, which is the second argument. It's a Boolean valued argument, so it can only take values true and false. And the default value is true, which means that we are sorting our data in an ascending order. I could have also skipped this argument. You can see in a bit that we are getting exactly the same result when we are mentioning this argument ascending equal to true and without mentioning this argument, simply because the default value is equal to true. So let's actually go ahead and remove this for one case and leave for the other, such that you can see that both will result in the same output. Here we go. So let's also add a line in between to make sure that we are getting everything nicely printed. Here we go. So as you can see here we are getting, as expected, Sana at the top and then Bob at the bottom. And in this way, you can verify that your sorting occurred successfully and you have done it in an ascending order, because the salary is increasing and the lowest salary is at the top and then the highest salary is at the bottom. So the other thing that you can see here is that we are getting exactly the same result when we are mentioning the ascending equal to true. So this is simply because there are certain arguments, and the arguments have certain default values in Python. And whenever you want to have the default value as your argument's value, you can also skip that argument, and you don't need to mention that specifically. Therefore, this results in the same output as this line. But if we do want to change the order, so we want to have another value corresponding to that argument, which is not a default value, then we need to change that. And we need to specifically mention what is the value that we want, which means that if we want to order this data, so we want to sort this data based on salary, but in a descending order, we need to use this argument. And instead the true, we need to change this to false. Because if the ascending is equal to false, it means that the descending is equal to true. Hope this makes sense. So let's go ahead and print this. Here we go. So as you can see now, we have exact opposite of what we had before. So we have now the highest earner, Bob, with the age of 20, with a salary of $220K from the tech department at the top. And then the salary would decrease accordingly. And then at the very bottom, we have Sana with an age of 19 with a salary of $10K from the operations department because she is earning the least. So this is about sorting. This is all what you need to know. Do keep in mind about this descending and ascending and how you can use the parameters in this function in order to sort your data accordingly. Another thing we are going to learn today is how to group your data. So let's say we want to group our data based on a department. So we want to know per department what is the number of employees. Or it can be that we want to obtain per department the average salary. Let's go ahead and learn how to do that in Python. So let's say we first count the number of people in a department. For that, what we need to do is to take the name of the department, of the data frame, which is data, and then dot. And what we need to do here is to use the function called group by. And this is a pandas function that we can use to group our data. And within group by, we need to specify the variable based on which we are doing the grouping. And as we want to obtain the number of employees per department, it means we are aggregating the data based on department. So here I will mention then the department, which is the variable we are using for grouping our data. And then next thing we need to do is to do dot and then the operation that we are performing. In this case, we are counting the number of employees. This means that I can either use the salary column, or I can use the age or the name in order to obtain the number of observations per department. So let's go ahead and do count By the way, we can also even skip this part, and we can specify that we want to just count the number of times the department name appears, because this also will go and calculate the number of employees per department. So let's go ahead and see what I mean here. Print. Then let's also add the closing parenthesis for the print. Here we go. So as you can see, we are getting as an index for this new data frame, the name of the department, so the variable that we use to do the grouping by. And then here we have healthcare, operations, and tech. What you are getting here is basically the number of times each of this department appear for the variable name, age, and salary. So as you can see, this is the column name, the first one, and then you have the age and then the salary. If we were to go ahead and actually specify the exact column that we want to do the grouping and then aggregation, so let's say the name, then we can expect to do the aggregation only based on the variable name. So as you can see, here we are getting this new data frame. And it says that the department healthcare got only one person working, and then the operations got 2, and then tech got 5. If you go ahead and count here, you can verify that information actually. So you have here tech once, 2, 3, 4, and 5, so 5 times. Then the healthcare once, and then the operations twice. Exactly what we got here. So in this way, you can do the you can count the number of times each of the observations appear based on the variable that you have chosen, and you can decide either to select a specific column to do the aggregation, or you can also leave that part and you just implement the function, and it will do the corresponding operation for all the columns. So for the name, for the age, and for the salary. So let's actually go ahead and calculate the average salary per department. For that, what I need to do is to change the name of the variable based on which I want to do the aggregation. And then instead of using the function count, I will use the function mean. And this function, so the mean is the same as the average, should calculate the mean or the average salary per department. And as you can see here, we are getting that the healthcare department has an average salary of 170K, operations has 20K as the average salary, and the tech has the 113K as the average salary. So one way you can verify that this information is really correct is, for instance, by looking at the healthcare. And this is an easy way to do that because healthcare got only one observation, and the average of the one observation is equal to that average, which means that if we look at the healthcare salary, so the only person who is from the healthcare department is the person with the name Alice, and then the corresponding salary is 170K, exactly the same number as we got here. We could also go and do the same calculation, only instead of calculating the average, we could calculate per department the minimum salary. So let's go ahead and do that. We see we are getting an error because we forgot a parenthesis in here. So now you get not the average, but the minimum salary per department. You could also do the maximum per department. You could also do the minimum age or the average age by department to see the age groups accordingly. So for that, what you had to do is to change the salary to a variable called age, because we want to do the aggregation based on age. And here we can then change minimum. And in this way, we can calculate the average age per department. So as you can see, from the Department of Tech, the people are on average 41 years old. From the Operations Department, they are on average 22 years old. And in the Healthcare Department, they are around 65 years old. And this is how you can do grouping in Python. And then the final part in this demo is to look into the filtering. So how we can use the filtering in Python in order to select data observations based on specific criteria. So let's say we want to keep only the name and the information of people in this data frame that got a salary higher than certain threshold. So let's say people whose salary is larger than 100K. So for that, what we need to do is, like always, mention the name of the data frame, which should be filtered. And then here, what we need to do is to add a square parenthesis. And within the square parenthesis, we need to specify the constraint. So the first part, so this part where we are specifying the name of the data frame and then the square parenthesis, this mentions that look into the data frame and select specific observations. So keep only those observations in this data frame. The second thing you need to mention within the square parenthesis is the actual condition that this observation should satisfy in order to be kept and not to be filtered out. For that, what we need to first do is to specify the condition and the column based on which the condition should be conducted. So data and then square parenthesis and then the name of the variable based on which we are doing the filtering is the salary. So therefore, we are saying look into this specific column, so data, salary, and then we are saying that the salary should be larger than 100,000. So in this way, what we are telling to Python to do is to look into the data frame data and then look into its salary column, select all the observations for which the salary is larger than 100,000, and then only provide the data corresponding to those observations. So let's go ahead and check it whether it is doing everything correctly. Here we go. So as you can see, we are removing all the observations from our data frame that do not have a salary higher than 100,000 and only keeping the observations whose salary is larger than the threshold. So as you can see, we no longer have, for instance, Anna in our data frame. We no longer have the Karen in our data frame, or the fifth observation, which corresponds to Kevin, and then Sana is also not included in our data, but only the people whose salary is larger than 110K are included in this data frame. So let's say we want to add an extra condition. So we not only want to have people whose salary is larger than 110,000, but we also want to filter out people whose salary is too high. For instance, whose salary is larger than 200K. And in this case, what we expect is from this data frame, Bob should be removed. So as you can see now, with this current filtering, Bob is still included. But then if we also remove the people whose salary is larger than 200K, then Bob should be removed. So let's go ahead and learn how to do multiple filtering. And here what we will use is the AND operation, because we want the two of the conditions mentioned here to be satisfied. So for that, we need to separate the conditions using this parenthesis. So then I will add here the second condition, which will be based once again on the variable called salary. And then we are saying that the salary should be smaller than 200,000. Here we go. So this symbol stands for AND. And as you can see now, we no longer get the information of the Bob because Bob got a salary above 200K. So in this way, you can specify not just one, but multiple conditions that your observation should satisfy in order to be filtered in this new data frame. And the final thing that we will look into is to how filter your data, not based on the larger or smaller, but based on specific values. So let's say you are interested in data of people whose age is equal to 65 and 20. So in this case, you can no longer say that the age should be larger than a certain value or smaller than a certain value. Or even if you do that, it will be much more complicated than to just help to Python to select all the observations for which the age is equal to this specific values. And in those cases, the is-in functionality comes very handy. So for that, what we need to do is to simply, once again, take the name of the data frame. And then here we'll be mentioning again the name of the variable that we need to look into, which is age. And then here we need to specify dot is in. And what this function basically does is that it looks into specific values for this age and only keeps the observation that's satisfied to those values. So in here, I mentioned that I want information only for people with an age of 65 and 20. For that, I need to put those two values within an array because they are not just one, but two values. Here we go. So as you can see, now we are getting only the data corresponding to people whose age is equal to 65 or 20. So this is how you can use the easing functionality to filter for specific values in your data. And this becomes even more handy when you are dealing with string type of variables. So you can no longer say that the corresponding column, the observations value should be larger than or smaller something because you are dealing with strings. And in those situations, the easing can be really handy. So it's really worth to know how to do the filtering based on specific values. And this is all for this demo where we learned about grouping, filtering, and sorting in Python. Stay tuned, and I will see you in the next demo. Hi there, and welcome to another demo. In this demo, we are going to talk about descriptive statistics. We are going to learn about calculating the mean, calculating the standard deviation, the variance, the mode, the median, different percentiles, quantiles for arrays, as well as we are going to learn how to get the descriptive statistics table for a pandas data frame. So descriptive statistics play a very important role in analyzing and summarizing your data. Here are a few reasons why I believe knowing how to calculate descriptive statistics is important and also how you can use it. So first of all, descriptive statistics help us to summarize our data. So descriptive statistics provides a concise summary of the main features of your dataset. It can help you to understand the data by providing measures such as the mean, dispersion, the variance, and the shape of the distribution. Summarizing your data will help you to gain more insights about your data in an efficient way, making it much easier to interpret as well as to communicate with other people during the presentations whenever you want to explain something about your data. And also, it's the essential part of every data science and data analytics project. The first thing you need to do is to obtain the descriptive statistics about your data and present it to your stakeholders in order to tell a story about your data. Another thing you can do with descriptive statistics is to perform data exploration. So descriptive statistics is a great way, a good starting point for exploring and understanding your data. It provides an overview of a data distribution. It can help you to identify certain patterns. It can help you to identify outliers by looking at the mean as well as the minimum and the maximum of your different variables. It can also help you to identify potential data issues. So the outliers, noise in your data, as well as missing values. It can also help you to understand the type of variables you are dealing with, because if you get an output from your descriptive statistics, you'll get an understanding whether you are dealing with a categorical string variables or numeric variable, or a floating data point, or an integer data point, etc. It will help you to further investigate your data and to have a good understanding of what should be your steps in order to clean your data and to prepare your data in the best possible way for your machine learning model. Another thing you can do by using descriptive statistics is to get an understanding whether the sample that you have sampled from the main population is a good representation of your population. So, as part of the fundamentals to statistics section in this course, we learned about the difference between sample and population and how we use sample, and we randomly sample a small part of your entire population in order to make conclusions about your population. But then the criteria is that your sample should be a true and an unbiased representation of your population. By using descriptive statistics, you can then compare, for instance, the mean and the variance of your sample to the actual population in order to get an understanding whether you are dealing with a good sample or whether you need to go back and then sample again in order to get a good sample. Another thing you can do is to visualize your data. So by using descriptive statistics, you can visualize your data in order to represent it to different stakeholders. You can use histograms, you can use box plots, you can use bar charts or pie charts in order to represent your data in a clear and understanding way. So without further ado, let's learn how to calculate different statistics for our array. So here I've created an array which consists of the following numbers. As you can see, 100, 25, 20, 45, minus 100, and 46. So first thing we are going to do is to calculate the mean. The mean is the average of a set of numbers, and in this case, it will be the mean of all these numbers, and it is calculated by summing up all these different numbers that we have here in this set and dividing it to the number of observations we got here. So as you can see, the length of this array is equal to 7, which means that we need to sum up all these values and divide it to 7, and this will be our mean or the average. We can do that by using the NumPy library. So np dot mean, and this is the function that will calculate the average. And then here within the parentheses, we need to specify what is that the variable or the array that we want to calculate the average. Let's calculate and let's see what that value is. So as you can see, the mean of this array is equal to 90.43. Next thing we are going to learn is how to calculate the median. So sometimes when we are dealing with sampling distributions, the sampling distribution might be skewed. So it can be left skewed or right skewed. For those cases, calculating the mean might not be the smartest thing to do, and therefore it would be better to calculate the median, because the median is then the better representation of the overall data instead of the mean. So it's usually handy to calculate both of them, the mean and the median. And whenever the mean is different from the median, it means that you are dealing with a skewed distribution. So the median is the middle value in a set of numbers when they are arranged in an ascending or descending order. If there is an even number of values, then the median is the average of the two middle elements. And the median is also the second quantile from the statistical terminology. So it's the 15th percentile. Let's go ahead and learn how to calculate the median for this array. So median underscore is equal to an np dot. As you can see, we are already getting the recommendation of the function called median, so very straightforward. And let's go ahead and print this. Median of array here we go. So as we can see, the median of this array is equal to 20. One thing that we can also see is that the mean is very close to the median, indicating that we most likely are not dealing with a skewed distribution. Next thing we are going to learn is how to calculate the mode. The mode is a value or the values in the set of provided numbers that occurs the most. So in our case, in our data array, we can see that there is a single value that appears the most, which is 2 times, and that's the value 20, and this is the mode. So in this, to calculate the mode of our array, we are going to use a different library. So we are not going to use the NumPy, and instead we are going to use the SciPy. So the reason for this is because NumPy does not contain this corresponding functionality to obtain the mode. And the reason for that is because mode is not a popular measure of central tendency. Usually we only calculate the median or the mean of the data, and we are good to go. But then if you want to calculate the mode, it's still useful to know how to use this corresponding library to do that. So let's go ahead and for that import from SciPy the library called stats. And then from here, we will use the stats.mode function to calculate the mode of our array. So as you can see, the output is slightly different, but the idea is the same. So as you can see that the mode of this array is this value. So 20. And it appears 2 times. So we are getting 2 outputs. We are getting the actual value, so the value that appears the most, and also how many times it appears, so count. And it's equal to 2 because we got 2 of those 20s in our data. The next thing we are going to learn is how to calculate the variance and the standard deviation. So variance measures the spreadness or the dispersion of the data. It quantifies how far your number is from the mean. And a higher variance indicates a greater variability in your data, and a lower variance indicates a smaller variability in your data. And standard deviation is highly related to the variance. The two are basically explaining the same thing, only standard deviation is the square root of the variance, and it is at the level of your numbers, which makes it more preferred whenever it comes to interpreting the results. It's the square root of the variance, as I mentioned, and it provides a standardized way to explain and understand the average distance between each data point and the mean. Therefore, it's almost always preferred to use standard deviation when you are explaining your data and how much variability is there in your data. So let's go ahead and use the NumPy library once again in order to calculate the variance and the standard deviation of this data. So variance underscore is equal to np.var and then data, and the standard deviation or the STD underscore is equal to np.std data. Let's go ahead and print it. The variance Here we go. As you can see, here we are getting the variance of our data and the standard deviation of our array. All right, so this is about calculating various statistics given the array. Another thing that would be worth to know is how to get the descriptive statistics whenever you are dealing with a data frame. So let's go ahead and bring our data that we used previously. So you might recall that we saw previously this data set describing the percentage of women that completed certain bachelor studies. Let's also import the pandas data frame, as we need that to load this data frame as well as to compute the descriptive statistics. So this is how the data looks like. And most of the time, whenever we are dealing with the pandas data frame, we want to get the nice descriptive statistics table that will describe our data. And we can simply do that by using this nice functionality in pandas. So we need to specify the name of the data frame and then describe, and this will go ahead and print for us the descriptive statistics of this data frame. Let's go ahead and print that. Here we go. So this is how the descriptive statistics table looks like when it comes to the pandas data frame. So we are getting the count, so the number of observations that we got per variable. Now we are getting the mean, which we just saw for an array. Now we are getting the mean per column in our data frame. Then we have the STD, which stands for the standard deviation. Then we got the mean, which is the minimum value per column in our data frame. Then we have the 25 percentile, which is the lowest 25th percentile in your column, which is basically the first quantile from the statistical point of view. And then we got the 15 percentile, which is the median, what we also just saw when we were calculating the median of array. 15 percentile is also the second quantile from statistical terminology. Then we got the 75th percentile, which is the third quantile. And then we got the maximum, which is the maximum corresponding to that column. So as you can see, this is a great way to summarize your data. So you can look, for instance, the year, and you can see that the minimum of the year is 1,970. The maximum is 2011, which means that you can say that you have a data spanning from 1970 till 2011. Then you have the mean. In case of year, it's not really meaningful, but when you look at other columns, for instance, when we look at the architecture, which describes the percentage of women that completed the study of architecture across different years, you can see that across the years, so spanning from 1970 till 2011, there were on average 34% women who completed this study. So in this way, you can then tell a story about your data, and you can also identify some problems in your data. So this is all for this demo, where we learned how to calculate different statistics for an array, as well as how to get the descriptive statistics table whenever we are dealing with a pandas data frame. So this is all for this demo, and I will see you in the next one. If you are looking for machine learning, deep learning, data science, or AI resources, then check out the free resources section in LunarTech.ai or our YouTube channel, where you can find more content and you can dive into machine learning and in AI. Hi there, and welcome to another demo. In this demo, we are going to learn how we can combine, so we can merge different tables that we have in our database. Because most often, we get our data not in one file, but in multiple files. And sometimes we need to do some preprocessing, some filtering, and then at the end, we need to join multiple tables together in order to end up with a single table, such that we can use that in our analysis, in our data visualization, and in our machine learning training process. And we will train our model only on a single data set. For that, you need to know what are all the different joins out there, what are the possible combinations, what are the possibilities, and how you can do each of them in Python. So in here, in this picture, you can see the most popular joins out there. And we have here a left join, we have an inner join, we have the right join, we have left anti-join and right anti-join. So in here, we will be looking at two tables. We have a table X, which will contain certain features and then certain observations. And then we will have a table Y, which will contain a different table with different observations and different features. And our goal is to merge these two tables in different ways. And the way we can do that, it really depends on what kind of join we want to do. So let's go each of these joins one by one. We will go into definition, and here we will use the idea and we will assume that there is one key. So there is a key identifier present both in table X and table Y that we can use in order to find out whether a certain observation exists in X and in Y or not. Because whenever we are trying to merge two tables, we need at least one key identifier to use that to do the merge on that. So let's say we have a table containing the sales of a shop, and then we have a table containing the customers of the shop. At least we need to know the identifier of a shop in order to say that this customer in this shop has bought this item, and then this shop had the corresponding sales. In this way, the shop identifier will be the key identifier to be used in order to merge this sales data with the customer data based on the shop. So using this idea, we will then look into these different joins. So first we will look into the inner join. And by definition, an inner join returns only the matching rows. So what you see here, the intersection between two tables based on a common column, which will be the key identifier. So if we have certain observations that are in table X, but then they are not in table Y, which means that we are talking about all these observations not highlighted. And if we have certain observations that are in table Y, but not in table X, so those are all this on this part of the Y that is not highlighted, then all these observations will not be included in the final joined table. And we will only end up with observations that are in this intersection. So they appear both in X and in Y. So in terms of the example that I just mentioned, it means that we will be only keeping the data for the shops for which we have both the sales information and the customer purchase information. The result will include only the rows where the key values will be present in both table X and in table Y. Let's now look into the left join. So in here, you can see the left join. And the definition of the left join is that a left join returns all the rows from the left table and the matching rows from the right table, in this case, table Y, based on the common column, so the key identifier. So if we have certain observations that we do not have information about in the table X, so those are all the observations in here. So in table Y that we do not have in table X, then those observations will not be included in the final output. And instead, all the observations in X, independent whether they are in table Y or not, they will be included. So basically, we are selecting all this part of the two joins. So this will be our output. So the result will include all rows from the left table, so table X, and the matching rows from the right table, so table Y. And if there is no match, it includes null values for the columns of the right table. So you will see some null values appearing in your end result, because there will be cases for which you can see that observation contains information in here from table X, but not from table Y. Then another interesting join to look into is the right join. Right join is basically the exact opposite of the left join. So right join returns all the rows from the right table, so table Y, and the matching rows from the left table, so table X, based on the common column. So those are all the matching rows, and those are all the rows that are only in table Y. And this will be the output of our table. And then we have the left anti-join and right anti-join. Left anti-join is very, it's kind of close to the left join, but it is basically the derivation from the left join and inner join. So unlike in the left join where we were including both the observations that were matching and observations that were only present in X, in case of left anti-join, we are only including, so the output will be only the observations which are not matching, and they are only in X. So this highlighted part. So by definition, left anti-join returns all the rows from the left table, so table X, that do not have a match in the right table based on the common column. So it will be only this part. And in case of right anti-join, it is the exact opposite of the left anti-join. So by definition, a right anti-join returns all the rows from the right table, so table Y, that do not have a match in the left table X based on a common column. So let's say we are looking at this example of a shop for which we have the sales information and for which we have the customer purchase information. If we only want to have the customer information for the shops that do not appear in the sales data, so the sales data is the table X, right? And the customer purchase data per shop is the table Y. And we want to only have information for the shops and their customer purchase information for which we do not have the corresponding sales data. So in those cases, you can then use the right anti-join. It might not be reasonable for this specific example, but sometimes whenever we are looking at samples in our database, sometimes using the left anti-join and right anti-join might be handy. Therefore, it's worth to know how to do that in Python. So here we have two different small data frames that I created in Python, data 1 and data 2. And in the first data frame, we have in total of 7 observations. So you can see A, B, C, D, E, F. And in the second one, we have the C, D, E, F, G, H. And the corresponding indices are from 8 till 13, whereas for the data 1, the indices are from 1 till 7. So note that we do not have any intersecting indices because we are going to merge this data, and we want to avoid case when we have a different value corresponding to the same index. So without further ado, let's first learn how to do an inner join between these two data frames. But before that, let's actually look into them. So let's print the data 1 and the data 2. And as you can see, here we are getting our two data frames. So you can see that this is the data 1 and this is the data 2. So what we are going to do is to learn how to do an inner join, so how to do a merge where our way of joining is the inner join. So for that, let's first call the corresponding data frame that we want to create. So merge and then inner join. And this will be equal. And here we are going to use the pandas merge function. So merge. And then whenever we are using this, we first need to specify the data frames that we want to merge. So in our case, it's data 1 and then data 2. And then what we need to do is to use the argument on to specify the key, so the identifier that we are going to use in order to merge the two data frames. In this case, it is the key because it does make sense to join the data frames on a variable which we do have something in common in the other table. And in this case, as you can see, we have certain rows. So for instance, the letter C, letter D, letter E, and F appear in both data 1 and data 2. And as we have only two variables, only one of them makes sense to be used as an identifier. So in here, we will use the key as our variable based on which we are going to do the join. And then we need to specify the exact way we want to do our join. So the inner join has the corresponding parameter of inner. So whenever you are writing inner as a value for an argument how, then Python understands that you want to do an inner join between data frame 1 and data frame 2. So let's go ahead and actually print this. So merge and then inner join. And before printing the output, let's actually understand what is the expected output. So there are common keys that appear both in data 1 and data 2. And those are the row corresponding to the key C, key D, and then E, and then F, and the G. So we expect that those keys that appear both in data 1 and data 2 and their corresponding values will then be in the inner join. So let's go ahead and print it. Here we go. So as you can see, as expected, we are getting the value 1 and value 2 corresponding to the key C, D, E, F, G in this output, because those are the ones that appear both in table data 1 and in table data 2. Another thing that we are going to learn is how to do a left join. So as we learned, left join will provide all the values that appear in the first table, in the left table, as well as all the matching values that appear both in the left table and in the right table. So what we need to do for that is basically to have the same, so left join. So let's rename it to avoid confusion. And then here, the only thing that we are going to do is to change this to left. Let's go ahead and print this. And this is our left join. So as you can see, we are getting all the values, so all the keys that we got in a data 1. And we are also getting all the keys that appear in data 2. So as you can see, in data 2, we got the key C, D, E, F, G. So those values, which also appear in here. You can see that the value 2 corresponding to 8, 9, 10, 11, and 12 also appear in here. But then the other values for which we do not have the matching observations in the table data 1, they do not appear in here. So here you can see that we have nonce corresponding to the key A and the B, because those keys do not appear in the second table, in the left table. So this is the output of the left join. As you can see, the variables that only appear in the right table, they end up getting some non-values, but all the fields and observations that were included in the first table, so data 1, they do appear in full in here. Now let's go ahead and do our right join. So as we just learned, right join is basically the opposite of the left join, which means that we can expect to get all the rows from the data 2, so the right table, but then some of the rows that were in data 1, but they were not in the data 2, they will not appear. So we will get only the matching ones and the ones that are present in the data 2. So let's also change the parameter in the argument. How? By right. And we should see some non-values in the value 1, because value 1 is a variable appearing in the data 1. So as expected, here we are getting all the matching keys that are both present in the table 1 and data 1 and data 2, as well as some non-values corresponding to the value 1, because this row does not appear in the data 1, but it is present in data 2. And then all the rows that are present in data 2 are in here. And finally, let's go and learn how to do left anti-join, and the right anti-join, I will leave it to you. But the idea should be the same, as it's in its concept, they are very similar. So in case of left anti-join, we need to go the extra mile and do some extra steps in order to get our left anti-join. So the first thing we are going to do is to do a left join. And then from the left join, we want to remove the intersection part. So if you bring back the diagram that we just saw, you might recall that in case of left anti-join, we are doing something very similar as the left join, only instead of also choosing the matching observations that appear both in the left and the right tables. In case of left anti-join, we are only selecting observations that appear in the left table, but not the matching observations. So we are removing the intersection part. Therefore, what we are first going to do is to do the left join. So let's call it merge and then left anti. It's equal to, and then pd.merge, so the same function. And here we are going to specify the left table and then the right table. And then once again, the on argument. Here we are specifying the variable based on which we are doing the join. And then how we are going to do the join, which is equal to left, as we want to do left anti. So first we want to do the left join. And we also this time want to save the indicators that come as a result from the joins. So by default, the indicator is actually set to false. And we are going to change that, and we are going to set it to true. And what this indicator does is that it shows whether the observation belongs to the left table only, or it belongs to the matching part. So it shows whether the observation was in the table data 1 only, or whether the observation belongs both to the data 1 and data 2. So it is in the intersection part. And then using this indicator and using this classification that will come from this indicator, we can then identify all the observations that were part of the intersection. And we can remove them, and we will end up with all the observations that belonged only to the left table, so the data 1. Exactly what is the point behind left anti-join. So let's go ahead and print the output of this table to show you what this indicator does. So as you can see, now we are getting pair observation beside of the left join of the two tables. We are also getting this underscore merge column, which says whether the observation belongs only to the left part or it belongs to the both parts. So it's in the matching, in the intersection zone. So as you can see, we got two observations. So observation with a key A and a B that belongs only to the table data 1. And those are the observations that we want to keep. And we want to remove all these observations from the intersection zone. So from the keys C, B, E, F, and G. All right. So next thing we are going to do is to define our left anti-join data. So let's do merge and then underscore left anti-join. Sure, let's make this left because it makes much more sense. And then we will use this data frame. And here we are going to apply the filtering that we learned previously. So we are going to say, look into the variable underscore merge that just came from the indicator and look into all the cases where this variable is equal to left underscore only. And this will then keep only the observations that appear in data 1. So let's go ahead and print this. And you will see that we will end up only keeping the observations for which the underscore merge will be equal to left underscore only. Here we go. And this is our left anti-join. Of course, we don't want to keep this underscore merge anymore because we have already used it. And there is no purpose of keeping it. So what I will do is I will drop it. So let's do it actually in a new line. I will put the name of the data frame. I will do dot and then drop. And then here I will do underscore merge because this is the variable that I want to drop. And I need to specify the axis. So as it's a column, I want to remove a column. I need to specify that the axis should be equal to 1. In Python, the axis equal to 0 means rows, and in axis equal to 1, it means column. As underscore merge is a column, I'm mentioning that axis equal to 1. And let's actually go ahead and overwrite this data frame as I want to keep just one copy of the data frame. And this is the output. Here we go. So this is our left anti-join. As you can see, it is a bit more complicated than the left join or the right join, but I think it's worth to know how to do it because sometimes it can be very useful to implement this in practice. So I will leave the right anti-join to you. And this actually completes our demo for today, where we learn how to do left join, inner join, right join, and also left anti-join. This is all, and I will see you in the next demo. Hi there, and welcome back to another demo. In this demo, we are going to learn how to perform data visualization with Matplotlib in Python. Data visualization is a very important technique for gaining insights from your data and to effectively communicate your findings to your audience, whether it's presenting to your stakeholders or whether it's putting in your case study or in your paper. It's really important to know how to plot those visuals by using Python because it's a simple way to go from your data analysis to your data visualization, which sometimes we call exploratory data analysis or EDA. And EDA sometimes can be the essential part of the case study to showcase your data, to find some correlations. It can be also a stepping stone towards the next step in your case study, whether it's causal analysis or modeling. It can help you to identify features that explain your dependent variable. It can help you to identify unimportant features, or it can help you to identify a noise in your data. So therefore, it's really important for you to know how to make those visuals. So the first type of visualization we are going to learn is the line plots. Line plots are a great way to visualize trends or patterns in the data. They are a great way to visualize time series. So whenever you are dealing with a graph where the x-axis in the form of a time, and then the y-axis are the values that evolve over time. This can be, for instance, the stock prices or the stock returns or the ROA of a company. You get the idea. So for that, what I have here is a set of x values and y values that I created in the form of an array. And what we're going to do now is to plot these arrays. So therefore, I've imported here the matplotlib pyplot library. So pyplot is a directory in the matplotlib library. And as a way of shortening the name of this library, is calling it PLT. So this is similar to the idea of using PD for the pandas and the NP for the NumPy. So let's go ahead and use that library. So it is PLT dot. And then we have plot. So PLOT. And then here we need to specify first the x values, and then we need to specify the y values. So the x underscore values, and then y underscore values. So the idea is that for each specific x, we need to have the corresponding y's. If your x array is different from the y array, which means that for certain x's, you don't have the corresponding y values or the other way around. So for certain y's, you don't have the x values, then you will get an error. So those two arrays should be the same. And for each x, you need to have the corresponding y values. So let's go ahead and run this, and you will quickly see that you are not getting any output. And the reason for that is because in Python, whenever you are using the pyplot library, you need to specify a PLT show such that your plot will actually be visualized. Here we go. So this is the plot that we are getting. As you can see, those are the x values starting from 1 and then ending with 10. And then the y value starting with 1 and then ending with 20. So as you can see, this plot is very basic. We don't have any extra information explaining it, but we want our plots to be self-explanatory. We don't want to add too much information, and we want our audience to look into the graph and the visuals and to understand what it's about. For that, you need to make use of extra functionalities in pyplot to add more information to your visuals. For instance, it would have been really handy to know what this x-axis represents, or what this y-axis represents, or to have a title on the top of the visual saying what this graph is about. All those can be done by using this PLT. And in here, we can say PLT dot and then x label. And this way, we can add a text to our x-axis, saying, for instance, what is the variable that the x-axis represents. So x-axis placeholder. And then the same we can do with the y-axis. Here we need to change y. Here we need to change y. So let's say you are visualizing the time series of stock prices, and your x-axis represents the time, and then the y-axis represents the stock prices. Well, in this case, you can then put in the x-axis placeholder that it is the date, and then the y-axis placeholder can be the stock price and then the name of the stock that you are looking into. And then finally, we can also add a title, plt.title. And here then you can put the title placeholder. For now, I will put it as text. But what you can do here is you can replace it with the title, let's say the stock prices or stock X from a time period X to Y. So in this way, you can then add more information to your graph. Let's see how this looks like in the actual visualization. Here we go. So here you have the title, here you have the text under the x-axis, and here you have the text beside of the y-axis. So another thing you can do is to work with your plot and to make it nicer. And you can do that by, for instance, changing the way the line is represented. So you can go from a line to dots. or dashes. It can be that you want to change the color of your plot. This one is really popular, and I think it's really worth to know. So, for instance, let's say your presentation is in the green color, so it's in the green palette, and you want your visual to match the color of your palette. What you can do for that is to use this argument color, and here you can, for instance, specify that it should be of green color. Here we go. So as you can see, this graph then changes the color. The plot is in the green, and this looks much more appealing compared to what we had before. All right, so this is about line plots. The next thing we are going to learn is how to plot scatter plots. Scatter plot can be really useful when we are trying to visualize a relationship between two variables. So let's say we have two features in our data, and we want to understand whether there is a certain relationship between the two, whether there is a correlation, because we want to know whether we have a strong, perfect correlation between the two, which is something that we need to check as part of the linear regression model. We don't want to have two features being multi-collinear and a perfect multi-collinear. And we also want to check sometimes the relationship between the feature and between the dependent variable, because we want them to be highly correlated. In all those cases, we can use then the scatter plots as a way to identify this correlation and to see whether there is a pattern or there is no pattern. And scatter plots can be, in those exact cases, super handy. So let's say we have exactly the same data, and instead of the line plot, we want to have the scatter plots. So for that, what we need to do is to do plt dot and then scatter. So instead of plot, we are using the function scatter. And then once again, we are specifying the x values and the y values. So let me go ahead and repeat the rest. Here we go. So as you can see, now we are getting the scatter plot. And this is basically the same plot that we saw before, only instead of lines, now we are getting dots. So this is a scatter plot coming from our first case study, where we were looking into the what factors make a playlist successful. And this is a vivid example of a scatter plot that helps us to understand whether there is a relationship between the number of albums in the playlist versus the average weekly active usage. And also you can see that there is a positive relationship, so in here. So in this way, using a scatter plot, you can identify whether there is a relationship between a pair of variables, whether it's your two independent variables, whether it's your one independent variable and your dependent variable. The next type of visualization we are going to learn is the bar chart. So how to plot bar charts in Python. And bar charts can be really useful for comparing different categorical values. So if you're dealing with a categorical data and you have a certain variable that has categories and you have the corresponding values, then you can visualize it nicely by using the bar charts. And for this, I've created here the sample data, a very basic one, where we have the categories of, in the terms of names of animals. So we have cat, we have dog, we have horse, and we have mouse. And then we have here categorical values. So this represents, for instance, the weight of animal. So this is the weight of a cat, weight of a dog, weight of a horse, and then weight of a mouse. And we want to visualize this. Let's go ahead and use once again the library and the function plt. So plt and then bar, which stands for bar chart. And here we need to first specify the categories, and then we need to specify the corresponding values. So cat and then values, which stand for categorical values. And once again, we need to add the label, we need to add the title, and we need to add plt show. So here we can replace this, for instance, by animals. And then here we can add, for instance, the weight of an animal. And then as a title, here we can say weight on weight hair animal. And finally, we want to do plt.show in order to show it. And I also would like to add a color to this visualization. So let's say I want the color to be forest green. By the way, if you're wondering what are all the possible colors that can be used for this argument color, then what you can simply do is to use the ChatGPT and try to search for different colors available in PyPlot and Matplotlib, and you will get the name of all the possible colors that you can use. And then you can use a nice color palette that matches your presentation or your case study. So let's go ahead and run this. So as you can see, we are getting this bar chart, this nice visualization, and we can see that the cat has the corresponding weight, and then we see the dog and the horse and the mouse. We can see, for instance, that the mouse has the smallest weight and the horse has the largest weight. And in this way, you can nicely visualize a categorical data. So let's now learn how to plot histograms. So histograms are useful for visualizing the distribution of numerical data. It can be that you want to visualize your population distribution, or you want to visualize your sample data, and you want to compare, for instance, your sampling distribution to the population distribution to know how your sample is representative of your population, whether it's an unbiased and a true representation of the population, which means that your sampling distribution should be close to your population distribution. So for all those kind of tests, you can definitely use the histograms. And by the way, this is a very common question asked during data science interviews when you are asked to randomly sample from a normal distribution or from a continuous uniform distribution and to plot this distribution in Python using histograms. Well, that's exactly what we are going to learn today. So you might recall from a demo where we learned how to randomly generate data and to create a simulated version of a data that we use this NumPy library to randomly sample from a normal distribution. And here we are sampling from a standard normal distribution with a mean of 0 and a standard deviation of 1. And here we are sampling 100 observations. So now we are going to plot this distribution by using histograms. And here, once again, I'm using plt dot, and then I'm specifying hist. And then here I need to specify the values that I want to plot. And then once again, I need to specify the X label. So as you can see here, we are getting our sample data. And here we have the frequency, so how often we are getting that corresponding value. And we can see that the distribution of the sample is symmetric around 0 as expected, because normal distribution is symmetric and it's well-shaped and it's always symmetric around its mean. And we sample data from the standard normal distribution with a mean of 0. And as you can see, the standard deviation, so how spread out the observations are from the mean, are very close to 1. So one thing that you will also notice is that as we increase this amount, so we increase the sample size, so we make it, for instance, 2000, then this distribution should look more and more, this histogram should look more and more like the actual normal distribution. Here we go. Let's actually go ahead and do something a bit more advanced to show you how this looks like when comparing the histogram with the plot. And what I want to do here is to visualize the sampling distribution. So when we are generating our own sample, randomly sampled from normal distribution, and we are comparing it to the actual population distribution by using this norm function that comes from the library called SciPy. And this one should be so-called population distribution, and what we had before should be the sampling distribution. Let's go ahead and plot this. Here we go. So here in this plot, as you can see, now we are no longer plotting the frequencies, but we are plotting the actual probability corresponding to the sampling distribution. And we are also in the same graph visualizing the population distribution. So the actual normal distribution with the same parameters. And the reason why I wanted to show this, because in this way, we can compare your population distribution to the sampling distribution. And one thing that you will see as you change the number of observations that you sample is that the higher will be the number of observations, so the sample size, more will this histogram, so the green bars will look like to the actual population distribution. And this is also the entire idea behind what we call central limit theorem. So if you're wondering what this normal distribution is, what the sampling distribution, population distribution, what the central limit theorem is, then head towards the fundamentals to statistics section of this course to learn everything about these topics. So one thing that you will notice in this specific graph is that we saw that there were also legend added to the visualization. So those are really helpful when you are plotting not just one, but two set of data sets in the same plot, and you want to explain what is the difference between them. In our case, we had this sampling distribution and we had a population distribution. And we had to specify that the bars correspond to the sampling distribution and the plot, so the line corresponds to the population distribution. Well, for that, we use what we call legend. And as you can see, the way that I'm doing it is by using plt.legend. And what I'm doing here is simply specifying the x values using the numpy arrange function, which arranges values between the minimum and the maximum, and then the corresponding incremental value. And then we have here the x values, which uses the norm function coming from the SciPy to generate the corresponding probability distribution values, so the probabilities. And then here I'm specifying the counts, the number of bins that I want to be visualized, and also what should be ignored. So here I'm using the histogram, and then I'm specifying the first the histogram that I want to plot, which is similar to what we had before. And the only difference is that I'm specifying that we are dealing with the density, which means that it's going to plot the probabilities instead of frequencies. Then I'm specifying the color, and then I'm specifying the label. So the way that the legend works is that I need to specify per plot what is the name of the plot by using this label argument. And then once you add all these labels and then you add here plt.legend, it will then per plot, so per type of visualization, it will then in the right corner or somewhere in the left corner, it will then specify the name of the plot. And if you want to see similar visualizations, how you can, for instance, randomly draw observations from Bernoulli distribution, from binomial distribution, exponential distribution, geometric distribution, normal distribution, Poisson distribution, or student T distribution, or uniform distribution, and how you can visualize them using the histograms, then head towards this GitHub repository that I will post as part of the resources, where you can see all those visualizations and their corresponding Python codes. And this is as part of this mathematics, statistics, or data science GitHub repository that I created. And this actually concludes this demo, where we'll learn how to create different visualizations in Python using Matplotlib. We'll learn how to do line plots, how to do scatter plots, how to do bar charts and histograms, and also how to combine, for instance, the plots and the histograms in a single visualization, one data point at a time. A/B testing is an important topic for data scientists to know because it's a powerful method for evaluating changes or improvements to the products or services. It allows us to make data-driven decisions by comparing the performance of two different versions of a product or a service, usually referred as treatment or a control. For example, A/B testing allows data scientists to measure the effectiveness of changes to a product or a service, which is important as it enables data scientists to make data-driven decisions rather than relying on intuition or assumptions. Secondly, A/B testing helps data scientists to identify the most effective changes to your product or a service, which is really important because it allows us to optimize the performance of a product or a service, which can then lead to increased customer satisfaction and sales. A/B testing helps us also to validate certain hypotheses about what changes will improve a product or a service. This is important because it helps us to build a deeper understanding of the customers and the factors that influence customers' behavior. Finally, A/B testing is a common practice in many industries such as e-commerce, digital marketing, website optimization, and many others. So data scientists who have knowledge and experience in A/B testing will be more valuable to these companies. No matter in which industry you want to enter as a data scientist and what kind of job you will be interviewed for, and even if you believe more technical data science is your cup of tea, be prepared to know at least high-level understanding and the details behind this method. It will definitely help you to know about this topic when you are speaking with product owners, stakeholders, product scientists, and other people involved in the business. Let's briefly discuss a perfect audience for this section of the course and prerequisites. There are no prerequisites of this section in terms of A/B testing concepts that you should know already, but knowing the basics in statistics, which you can find in the Fundamentals to Statistics section, is highly recommended. This section will be great if you have no prior A/B testing knowledge and you want to identify and learn the essential A/B testing concepts from scratch. So this will help you to prepare for your job interviews. It will also be a good refresher for anyone who does have A/B testing knowledge but who wants to refresh their memory or want to fill in the gaps in their knowledge. In this lecture, we will start off the topic about A/B testing, where we will formally define what A/B testing is, and we will look at the high-level overview of A/B testing process step by step. By definition, A/B testing or split testing is originated from the statistical randomized control trials and is one of the most popular ways for businesses to test new UX features, new versions of a product, or an algorithm to decide whether your business should launch that new UX feature or should productionalize that new recommender system, create that new product, that new button, or that new algorithm. The idea behind A/B testing is that you should show the variated or the new version of the product to a sample of customers, often referred as experimental group, and the existing version of the product to another sample of customers, referred as control group. Then the difference in the product performance in experimental versus control group is tracked to identify the effect of these new versions of the product on the performance of the product. So the goal is then to track the metric during the test period and find out whether there is a difference in the performance of the product and what type of difference is it. The motivation behind this test is to test new product variants that will improve the performance of the existing product and will make this product more successful and optimal, showing a positive treatment effect. What makes this testing great is that businesses are getting direct feedback from their actual users by presenting them the existing versus the variated product version, and in this way they can quickly test new ideas. In case of A/B test shows that the variated version is not effective, at least businesses can learn from this and can decide whether they need to improve it or need to look for other ideas. Let us go through the steps included in the A/B testing process, which will give you a higher-level overview into the process. The first step in conducting A/B testing is stating the hypothesis of the A/B test. This is the process that includes coming up with business and statistical hypotheses that you would like to test with this test, including how you measure the success, which we will call primary metric. Next step in A/B testing is to perform what we call power analysis and design the entire test, which includes making assumptions about the most important parameters of the test and calculate the minimum sample size required to claim statistical significance. The third step in A/B testing is to run the actual A/B test, which in practical sense for the data scientist means making sure that the test runs smoothly and correctly, collaborate with engineers and product managers to ensure that all the requirements are satisfied. This also includes collecting the data of control and experimental groups, which will be used in the next step. Next step in A/B testing is choosing the right statistical test, whether it is z-test, t-test, chi-square test, etc., to test the hypothesis from the step 1 by using the data collected from the previous step, and to determine whether there is a statistically significant difference between the control versus experimental group. The fifth and the final step in A/B testing is continuing to analyze the results and find out whether besides statistical significance, there is also practical significance. In this step, we use the second step's power analysis, so the assumptions that we made about model parameters and the sample size, and the fourth step's results to determine whether there is a practical significance beside of the statistical significance. This summarizes the A/B testing process at a high level. In the next couple of lectures, we will go through the steps one at a time. So buckle up and let's learn about A/B testing. In this lecture number 2, we will discuss the first step in A/B testing process. So let's bring our diagram back. As you can recall from the previous lecture, when we were discussing the entire process of A/B testing at a high level, we saw that in the first step in conducting A/B testing is stating the hypothesis of A/B test. This process includes coming up with a business and statistical hypothesis that you would like to test, with this test including how you measure the success, which we call a primary metric. So what is the metric that we can use to say that the product that we are testing performs well? First, we need to state the business hypothesis for our A/B test from a business perspective. So formally, business hypothesis describes what the two products are that being compared and what is the desired impact or the difference for the businesses. So how to fix a potential issue in the product where a solution of these two problems will influence what we call a key performance indicator or the KPI of the interest. Business hypothesis is usually set as a result of brainstorming and collaboration of relevant people on the product team and data science team. The idea behind this hypothesis is to decide how to fix a potential issue in the product where a solution of these problems will improve the target KPI. One example of business hypothesis is that changing the color of Learn More button, for instance, to green will increase the engagement of the web page. Next, we need to select what we call primary metric for our A/B testing. There should be only one primary metric in your A/B test. Choosing this metric is one of the most important parts of A/B tests, since this metric will be used to measure the performance of the product or feature for the experimental and control groups, and then will be used to identify whether there is a difference or what we call statistically significant difference between these two groups. By definition, primary metric is a way to measure the performance of the product being tested in the A/B test for the experimental and control groups. It will be used to identify whether there is a statistically significant difference between these two groups. The choice of the success metric depends on the underlying hypothesis that is being tested with this A/B test. This is, if not the most, one of the most important parts of the A/B test, because it determines how the test will be designed and also how well the proposed ideas perform. Choosing poor metrics might disqualify a large amount of work or might result in wrong conclusions. For instance, the revenue is not always the end goal. Therefore, in A/B testing, we need to tie up the primary metric to the direct and the higher level goals of the product. The expectation is that if the product makes more money, then this suggests the content is great. But in achieving that goal, instead of improving the overall content of the material and writing, one can just optimize the conversion funnels. One way to test the accuracy of the metric you have chosen as your primary metric for your A/B test could be to go back to the exact problem you want to solve. You can ask yourself the following question, what I tend to call the metric validity question. So if the chosen metric were to increase significantly while everything else stays constant, would we achieve our goal and would we address our business problem? Is it higher revenue? Is it higher customer engagement? Or is it high views that we are chasing in the business? So the choice of the metric will then answer this question. Though you need to have a single primary metric for your A/B test, you still need to keep an eye on the remaining metrics to make sure that all the metrics are showing a change and not only the target one. Having multiple metrics in your A/B test will lead to false positives, since you will identify many significant differences while there is no effect, which is something you want to avoid. So it's always a good idea to pick just a single primary metric, but to keep an eye and monitor all the remaining metrics. So if the answer to the metric validity question is higher revenue, which means that you are saying that the higher revenue is what you are chasing and better performance means higher revenue for your product, then you can use as your primary metric what we call a conversion rate. Conversion rate is a metric that is used to measure the effectiveness of a website, a product, or a marketing campaign. It is typically used to determine the percentage of visitors or customers who take a desired action, such as making a purchase, filling out a form, or signing up for a service. The formula for conversion rate is equal to number of conversions divided to number of total visitors multiplied by 100%. For example, if a website has 1,000 visitors and 50 of them make a purchase, the conversion rate would be equal to 50 divided to 1,000 multiplied by 100%, which gives us 5%. This means that our conversion rate in this case is equal to 5%. Conversion rate is an important metric because it allows us and businesses to measure the effectiveness of their website, a product, or a marketing campaign. It can help businesses to identify areas for improvement, such as increasing the number of conversions or improving the user experience. Conversion rate can be used for different purposes. For example, if a company wants to measure the effectiveness of an online store, the conversion rate would be the percentage of visitors who make a purchase. And on the other hand, if a company wants to measure the effectiveness of landing page, the conversion rate would be the percentage of visitors who fill out a form or sign up for a service. So if the answer to the metric validity question is higher engagement, then you can use the click-through rate or CTR as your primary metric. This is, by the way, a common metric used in A/B testing whenever we are dealing with e-commerce product, search engine, recommender system. Click-through rate, or the CTR, is a metric that measures the effectiveness of a digital marketing campaign or the user engagement or some feature on your web page or your website, and is typically used to determine the percentage of users who click on a specific link or a button or call to action, CTA, out of the total number of users who view it. The formula for the click-through rate can be represented as follows. So the CTR is equal to number of clicks divided to number of impressions multiplied by 100%. Not to be confused with click-through probability, because there is a difference between the click-through rate and click-through probability. For example, if an online advertisement receives 1,000 of impressions, which means that we are showing it to the customers for the 1,000 times, and there were 25 clicks, which means 25 out of all these impressions resulted in clicks, this means that the click-through rate for this specific example would be equal to 25 divided to 1,000 multiplied by 100%, which gives us 2.5%. This means that for this particular example, our click-through rate is equal to 2.5%. Click-through rate is an important metric because it allows businesses to measure the effectiveness of their digital marketing campaigns and the user engagement with their website or web pages. High click-through rate indicates that a campaign or the web page or a feature is relevant and appealing to the target audience because they are clicking on it, while low click-through rate indicates that a campaign or the web page needs an improvement. Click-through rate can be used to measure the performance of different digital marketing channels, such as paid search, display advertising, email marketing, and social media. It can also be used to measure the performance of different ad formats, such as text advertisements, banner advertisement, video advertisements, etc. Next, and the final task in this first step in the process of A/B testing is to state a statistical hypothesis based on the business hypothesis and the chosen primary metric. Next, and in the final task in this first step of the A/B testing process, we need to state the statistical hypothesis based on the business hypothesis we stated and the chosen primary metric. In the section of Fundamentals to Statistics of this course, in lecture number 7, we went into details about statistical hypothesis testing, including what null hypothesis is and what alternative hypothesis is. So do have a look to get all the insights about this topic. A/B testing should always be based on a hypothesis that needs to be tested. This hypothesis is usually set as a result of brainstorming and collaboration of relevant people on the product team and data science team. The idea behind this hypothesis is to decide how to fix a potential issue in a product where a solution of these problems will influence the key performance indicators or the KPI of interest. It's also highly important to make prioritization out of a range of product problems and ideas to test. Well, you want to pitch that fixing this problem would result in the biggest impact for the product. We can put the hypothesis that is subject to rejection, so that we want to reject in the ideal world, under the null hypothesis, what we define by H0. While we can put the hypothesis subject to acceptance, so the desired hypothesis that we would like to have as a result of A/B testing, under the alternative hypothesis, defined by H1. For example, if the KPI of the product is to increase the customer engagement by changing the color of the Read More button from blue to green, then under the null hypothesis, we can state that click-through rate of Learn More button with blue color is equal to the click-through rate of green button. Under the alternative, we can then state that the click-through rate of the Learn More button with green color is larger than the click-through of the blue button. So ideally, we want to reject this null hypothesis and we want to accept the alternative hypothesis, which will mean that we can improve the click-through rate, so the engagement of our product, by simply changing the color of the button from blue to green. Once we have set up the business hypothesis, selected the primary metrics, and stated the statistical hypothesis, we are ready to proceed to the next stage in the A/B testing process. In this lecture, we will discuss the second step in A/B testing process, which is designing the A/B test, including the power analysis and calculating the minimum sample sizes for the control and experimental groups. Stay tuned, as this is a very important part of A/B testing process, commonly appearing during the data science interviews. Some argue that A/B testing is an art, and others say that it's a business-adjusted common statistical test. But the borderline is that to properly design this experiment, you need to be disciplined and intentional, while keeping in mind that it's not really about testing, but it's about learning. Following are the steps you need to take to have a solid design for your A/B test. So let's bring the diagram back. So in this step, we need to perform the power analysis for our A/B test and calculate the minimum sample size in order to design our A/B test. A/B test design includes 3 steps. The first step is power analysis, which includes making assumptions about the model parameters, including the power of the test, the significance level, etc. The second step is to use these parameters from power analysis to calculate the minimum sample size for the control and experimental groups. And then the final third step is to decide on the test duration depending on several factors. So let's discuss each of these topics one by one. Power analysis for A/B testing includes these 3 specific steps. The first one is determining the power of the test. This is our first parameter. The power of the statistical test is the probability of correctly rejecting the null hypothesis. Power is the probability of making a correct decision, so to reject the null hypothesis when the null hypothesis is false. If you're wondering what is the power of the test, what is these different concepts that we just talked about, what is this null hypothesis, and what does it mean to reject the null hypothesis, then head towards the fundamentals to the statistics section of this course, as we discuss this topic in detail as part of that section. The power is often defined by 1 minus beta, which is equal to the probability of not making a type 2 error, where type 2 error is the probability of not rejecting the null hypothesis, while the null is actually false. It's common practice to pick 80% as the power of the A/B test, which means that we allow 20% of type 2 error. And this means that we are fine with not detecting, so failing to reject the null hypothesis 20% of the time, which means that we are fine with not detecting a true treatment effect while there is an effect, which means that we are failing to reject the null. However, the choice of a value of this parameter depends on the nature of the test and the business constraints. Secondly, we need to determine a significance level for our A/B test. The significance level, which is also the probability of type 1 error, is the likelihood of rejecting the null, hence detecting a treatment effect while the null is actually true, and there is no statistically significant impact. This value, often defined by a Greek letter alpha, is the probability of making a false discovery, often referred to as a false positive rate. Generally, we use a significance level of 5%, which indicates that we have 5% risk of concluding that there exists a statistically significant difference between the experimental and control variant performances when there is no actual difference. So we are fine by having 5 out of 100 cases detecting a treatment effect while there is no effect. It also means that you have a significant result difference between the control and the experimental groups within 95% confidence. Like in the case of the power of the test, the choice of the alpha is dependent on the nature of the test and the business constraints that you have. For instance, if running this A/B test is related to high engineering costs, then the business might decide to pick a high alpha, such that it would be easier to detect the treatment effect. On the other hand, the implementation costs of the proposed version in production are high. You can then pick a lower significance level, since this proposed feature should really have a big impact to justify the high implementation costs. So it should be harder to reject the null hypothesis. Finally, as the last step of power analysis, we need to determine a minimum detectable effect for the test. The last parameter as part of the power analysis we need to make assumptions about is what we call minimum detectable effect, or delta. From the business point of view, so what is the substantive to the statistical significance that the business wants to see as a minimum impact of the new version to find this variant investment worthy? The answer to this question is, what is the amount of change we aim to observe in a new version's metric compared to the existing one to make recommendations to the business that this feature should be launched in the production, that it's investment worthy. An estimate of this parameter is what is known as a minimum detectable effect, often defined by a Greek letter delta, which is also related to the practical significance of the test. So this MDE, or the minimum detectable effect, is a proxy that relates to the smallest effect that would matter in practice for the business, and it's usually set by stakeholders. As this parameter is highly dependent on the business, there is no common level of it. Instead, so this minimum detectable effect is basically the translation from statistical significance to the practical significance. And here we want to see and we want to answer the question, what is this percentage increase in the performance of the product that we want to experiment with that will tell to the business that this is good enough to invest in this new feature or in this new product. And this can be, for instance, 1% for one product, it can be 5% for another one. And it really depends on the business and what is the underlying KPI. A popular reference to the parameters involved in the power analysis for A/B testing is like this. So 1 minus beta for the power of the test, alpha for the significance level, delta for the minimum detectable effect. To make sure that our results are repeatable, robust, and can be generalized to the entire population, we need to avoid p-hacking to ensure real statistical significance and to avoid biased results. So we want to make sure that we collect enough amount of observations and we run the test for a minimum predetermined amount of time. Therefore, before running the test, we need to determine the sample size of the control and experimental groups, as well as later on in this lecture we will see also how long we need to run the test. So this is another important part of A/B testing, which needs to be done using the defined power of the test, which was the 1 minus beta, the significance level, and a minimum detectable effect. So all the parameters that we decided upon when conducting the power analysis. Calculation of the sample size depends on the underlying primary metric as well that you have chosen for tracking the progress of the control and experimental versions of the product. So we need to distinguish here two cases. So when discussing the primary metric, we saw that there are different ways that we can measure the performance of different types of products. If we are interested in engagement, then we are looking at a metric such as click-through rate, which is in the form of averages. So the case one will be where the primary metric of A/B testing is in the form of a binary variable. It can be, for instance, conversion or no conversion, click or no click. And in case 2, where the primary metric of the test is in the form of proportions or averages, which means mean order amount or mean click-through rate. For today, we will be covering only one of these cases, but you can find more details on the second case in my blog, which I posted also as part of the resources section. This blog post contains all the details that you need to know about A/B testing, including the statistical tests and their corresponding hypotheses, the descriptions of different primary metrics that go beyond what we have covered as part of this section, as well as many more details that you need to know about A/B testing. So let's look at the case 2 where the primary metric of the test is in the form of proportions or averages. So let's say we want to test whether the average click-through rate of control is equal to the average click-through rate of experimental group. And under H0, we have that the mu control is equal to mu experimental, and under H1, we have that the mu control is not to mu experimental. So here, the mu control and mu experimental are simply the average of the primary metric for control group and for the experimental group respectively. So this is the formal hypothesis we want to test with our A/B test. And we can assume that this mu control is, for instance, the click-through rate of the control group, and the mu experimental is the click-through rate of the experimental group. So this is the formal statistical hypothesis we want to test with our A/B test. If you haven't done so, I would highly suggest you to head towards the Fundamentals to Statistics section of this course, where in lecture number 7 and 8 of the statistical part of this course, I go in detail about statistical hypothesis testing, the means, averages, significance level, etc. This also holds for the theorem that the sample size calculation is based upon, called central limit theorem. So check out the last lecture about inferential statistics, where I cover the central limit theorem, which we will also use in this section. And finally, also check the lecture number 5 in that section, where we cover the normal distribution, another thing that we will use as part of this section. So the central limit theorem states that given a sufficiently large sample size from an arbitrary distribution, the sample mean will be approximately normally distributed, regardless of the shape of the original population distribution. This means that the distribution of the sample means will be approximately normal if we take a large enough sample, even if the distribution of the original sample is not normal. So when we are dealing with a primary performance tracking metric that is in the form of average, such as this one that we are covering today, which is the click-through rate, we intend to compare the means of the control and experimental groups. Then we can use the central limit theorem and state that the mean sampling distribution of both control and experimental groups follow normal distribution. Consequently, the sampling distribution of the difference of the means of these two groups also will be normally distributed. So this can be expressed like this, where we see that the mean of the control group and mean of the experimental group follows normal distribution with mean mu control and mu experimental respectively, and then with the variance of sigma control squared and sigma experimental squared respectively. Though derivation of this proof is out of the scope of this course, we can state that the difference between the means of the two groups, so x bar control minus x bar experimental, also follows normal distribution, with the mean mu control minus mu experimental, and with the variance of sigma control squared divided to n control, plus sigma experimental squared divided to n experimental. So the sample size of the experimental group and the sample size of the control group. Hence, the sample size needed to compare the means of the two normally distributed samples using a two-sided test with pre-specified significance level alpha, power level, and minimum detectable effect can be calculated as follows. So here you can see the mathematical representation of the minimum sample size. So the n, which stands for the minimum sample size, is equal to, and in the denominator we have sigma control squared plus sigma experimental squared multiplied by z1 minus alpha divided to 2 plus z1 minus beta squared divided to the delta squared. And here, the alpha and the beta and the delta, we have made assumptions about as part of the power analysis. And the sigma control squared and the sigma experimental squared are the estimates of the variance that we can come up with using the so-called AA testing. I would say you do not necessarily need to know this derivation, as there are many online calculators that will ask you for the alpha, the beta, and the delta values, as well as the sample estimates for the sigma squared control and experimental, and then these calculators will automatically calculate the minimum sample size for you. If you're wondering what this AA testing is and how we can come up with the sigma control squared and sigma experimental squared, as well as all the other values, then make sure to check out the blog that I posted before and that I mentioned before, as I explain in detail all these values, as well as check out the resource section where I've included many resources regarding this. But for now, just keep in mind that the z1 minus alpha divided to 2 and z1 minus beta are just two constants and come from the normal distributed and standard normal distributed tables. I would say you do not necessarily need to know this derivation, as there are many online calculators that will ask you for this alpha, beta, and delta values, as well as the sample estimates for the sigma squared control and sigma experimental control, and then will calculate automatically the sample size for you for the control and experimental group respectively. One example of such calculator is this A/B testing online calculator, but if you Google it, you will find many others that will ask you for the minimum detectable effect, for the statistical significance or the statistical power, and then it will automatically calculate for you the minimum sample size that you should have in order to have a statistical significance and in order to have a valid A/B test. One thing to keep in mind is that you will notice that the statistical significance level is set to 95% in here, which is not what we have seen when we were discussing the alpha or significance level. So sometimes these online calculators will confuse or will interchangeably use the significance level versus the confidence level, which are the opposite. So the significance level is usually at the level of 5% or 1%. Confidence level is around 95%, so which is basically 100% minus the alpha. Therefore, whenever you see this 95%, know that this means that your alpha should be 5%. So it's really important to understand how to use this calculator, not to end up with the wrong minimum sample size, conduct an entire A/B test, and then at the end realize that you have used the wrong significance level. The final step is to calculate the test duration. This question needs to be answered before you run your experiment and not during the experiment. Sometimes people stop the test when they detect statistical significance, which is what we call p-hacking, and that's absolutely not what you want to do. To determine the baseline of a duration time, a common approach is to use this formula. As you can see, duration is equal to n divided to the number of visitors per day, where n is your minimum sample size that we just calculated in the previous step. And the number of visitors per day is the average number of visitors that you expect to see as part of your experiment. For instance, if this formula results in 14 days, or 14, this suggests that running the test for 2 weeks is a good idea. However, it's highly important to take many business-specific aspects into account when choosing the time to run the test and for how long you need to run it, and simply using this formula is not enough. For example, if you want to run an experiment at the end of the month December with Christmas breaks, when higher than expected or lower than expected number of people are usually checking your web page, then this external and uncertain event had an impact on the page usage. For some businesses, this means For example, if you want to run an experiment at the end of the month of December with Christmas breaks, when higher than expected or in some cases lower than expected number of people are usually checking the web page, so depending on the nature of your business or the product, then this external and uncertain event can have an impact on the page usage for some businesses, which means that for some businesses, a high increase in the page usage can be the result, and for some, a huge decrease in usability. In this case, running A/B tests without taking into account this external factor would result in inaccurate results, since the activity period would not be a true representation of a common page usage, and we no longer have this randomness, which is a crucial part of A/B testing. Besides this, when selecting a specific test duration, there are a few other things to be aware of. Firstly, too small test duration might result in what we call novelty effects. Users tend to react quickly and positively to all types of changes independent of their nature. So it's referred as a novelty effect, and it wears off in time and is just considered illusionary. So it would be wrong to describe this effect to the experimental version itself and to expect that it will continue to persist after the novelty effect wears off. Hence, when picking a test duration, we need to make sure that we do not run the test for too short amount of time period, otherwise we can have a novelty effect. Novelty effect can be a major threat to the external validity of an A/B test, so it's important to avoid it as much as possible. Secondly, if the test duration is too large, then we can have what we call maturation effects. When planning an A/B test, it's usually useful to consider a longer test duration for allowing users to get used to a new feature or product. In this way, one will be able to observe the real treatment effect by giving more time to returning users to cool down from an initial positive reaction or a spike of interest due to a change that was introduced as part of a treatment. This should help to avoid novelty effect and is better predictive value for the test outcome. However, the longer the test period, the larger is the likelihood of external effects impacting the reaction of the users and possibly contaminating the test results. If you like this content, make sure to check all the other videos available on this channel. And don't forget to subscribe, like, and comment to help the algorithm to make this content more accessible to everyone across the world. And if you want to get free resources, make sure to check the free resources section at LunarTech.ai. And if you want to become a job-ready data scientist and you are looking for this accessible bootcamp that will help you to make you job-ready data scientist, consider enrolling to the Data Science Bootcamp. the Ultimate Data Science Bootcamp at LunarTech.ai, you will learn all the theory, the fundamentals to become a job-ready data scientist. You will also implement the learned theory into real-world, multiple data science projects. Besides this, after learning the theory and practicing it with the real-world case studies, you will also prepare for your data science interviews. And if you want to stay up to date with the recent developments in tech, what are the headlines that you have missed in the last week? What are the open positions currently in the market across the globe? And what are the tech startups that are making waves in the tech? And sure to subscribe to the Data Science and AI newsletter from LunarTech. This is what we call maturation effect. And therefore, running the A/B test for too short amount of time or too long amount of time is not recommended. As it's a very involved topic, we can talk for hours about this part of the A/B test, and also a topic that is asked a lot during the data science and product scientist interviews. Therefore, I highly suggest you to check out this blog about A/B testing, which is a hands-on tutorial about everything you need to know about A/B testing, as well as check out the interview preparation guide in this section that contains 30 most popular A/B testing related questions you can expect during your data science interviews. Looking to elevate your data science or data analytics portfolio? Then you are in the right place. With this A/B testing end-to-end case study, you can showcase your A/B testing and coding skills in one place. I'm Tatev and Vahe, data scientist and AI professional, and I'm the co-founder of LunarTech, where we are making data science and AI accessible to everyone, individuals, businesses, and institutions. In this case study, we are going to complete an end-to-end case study with A/B testing, where we are going to test in a data-driven way whether it's worth to change one of our features in our UX design in the LunarTech's landing page. This is a real-life data science case study that you can conduct, and you can put it on your resume in order to showcase your experience in data-driven decision-making, where you will showcase your statistical skills, experimentation skills with A/B testing, and your coding skills in Python using libraries such as stats models, but also the pandas, NumPy, also matplotlib, and Seaborn. We are going to start with the business objective of this case study. Then we are going to translate the business objective into a data science problem. Then we are going to start with the actual coding. We are going to load libraries, we are going to look into the data, visualize the data, the click data. We are going to look into the motivation behind choosing that specific primary metric, which is the click-through rate. Then we are going to talk about the statistical hypothesis for our A/B testing. I will also teach you step by step all the calculations, starting from the calculation of the pooled estimate from the click-through rate, and then a computation of the pooled variance, the standard error, but also the motivation behind choosing the search or statistical test that I will be using, such as the two-sample z-test, and then how you can calculate the test statistics, how you can calculate the p-value of this test statistics, and then use that with the statistical significance to test the statistical significance of your A/B test. After this, we will also then compute the confidence interval, comment on the generalizability of the A/B test, and then at the end, we will also test for the practical significance of the A/B test. Then we will conclude and we will wrap up, and we will make a decision based on our data-driven approach, using the A/B test to check whether it's worth it to change a feature in our UX design in the LunarTech's landing page. So without further ado, let's get started. So let's now start our case study. In here, I have in the left-hand side this version of our landing page, which is our control version, so to say the existing version, where you can see that here we have start free trial, and here we got as our button secure free trial. In the right-hand side, we got this new experimental version that we would like to have, which is the enroll now button. So as we saw in the introduction, what we are trying to understand is that whether our customers click more on the new version, the experimental version, versus the existing version, the control version. So as of the day of loading this and conducting this case study, our landing page has a secure free trial. But what we wanted to test with our data is whether the enroll now is more engaging, such that we can go from the secure free trial version to the enroll now version. And here, for this specific case, not only, but also in general, as we know from A/B testing, is that whenever we got an existing algorithm or existing feature, existing button, then we are referring this group that we will, where we will expose this existing version of the product, we are referring this as a control group. So all the users to whom we will show the existing version of our landing page, we will refer them as the control group participants. And then we have in the right-hand side our experimental version, and our experimental users, so the users, our existing customers that are selected to be taken part in our experimental group and in our experiment, they will be then exposed to this new version of our landing page, which contains this Enroll Now button. So our end goal in terms of the business, as we saw in the introduction, is to understand whether we should release the new button, which will end up being higher engaging, which means that we will have higher CTR or higher, more clicks that will come from our user side, which automatically means better business, because we want to have highly engaging users. If they are clicking on this button, it means that it interests them more compared to the control version. And if something on our landing page, in this case our call to action, is more interesting and highly engaging, it means that we are doing something right, and our users might either make use of our free products or purchase our products, or just stay engaged with us to keep LunarTech in mind. And whenever there is someone who is interested in data science or AI solutions or products, then they can at least refer their friends if they are just clicking to understand and to learn more about our products. That's also a possibility. So from a business perspective, we therefore are using here as our primary metric our click-through rate, the CTR of this specific button, which in our control version is the secure free trial, and in our experimental version is the enroll now. And what we want to understand is that whether this new button will end up having higher CTR or not, because higher CTR from the technical perspective will translate to higher engagement from the business perspective. So here we are making this translation from business versus technical. When it comes to A/B testing, we can have different sorts of primary metrics. We can have a click-through rate as a primary metric. We can have a conversion rate as a primary metric, or any other primary metric. What we want to have as our metric that will work as the single measure that will compare our control and experimental group to understand which version performs better is first to understand what this definition of better is and how that translates back to the business. Because if the engagement is what we are referring as better business for some reason, and I will explain you in a bit why we think the engagement in this case is what matters for us at LunarTech, then it means that click-through rate can be used as a primary metric. This is just a universal metric that has been used across different web applications, search engines, recommender systems, and many other digital products to understand whether the engagement of that specific algorithm, feature, web design, whether that is better or not. And in this case, in this specific case study, we are also going to use the CTR because we are interested in the engagement. So at LunarTech, we really care about the engagement with our users. And we want our users to make use of our products, but ultimately to engage with us. Because if they engage with us, it means that our products are being seen, our landing page is being visited, and the user is actually interested to click on that button and then the action point, and then to start either a free trial or to enroll to see what is going on, because all these are signs of interest coming from the user side. And in the control version, as our click to action is to secure a free trial, which directly lends the user to our free trial, to our Ultimate Data Science Bootcamp. But given that we are expanding, which means that we are now offering more courses, we are offering free products, and also we have enterprise clients, we have businesses as clients who want data science and AI solutions and who want corporate training. Therefore, we want to go from this niche version of a landing page, so secure free trial, to enroll now, because we already have a lot of engagement in terms of the free trial. We want to make it more general. So that's the business perspective. And on the other hand, we also want to change, beside of changing this main call action, we want to make it generalized. And at the same time, we want to see whether this generalized version will end up leading us a higher engagement, not only in terms of the other products, but also for the free trial itself. Because we always are looking for educating people and providing this free trial such that they can make use of our flagship product, which is the Ultimate Data Science Bootcamp. So now when we understand why we care about the engagement here at LunarTech, and we understand why we want to check whether this new button in our UX design will end up increasing the engagement or not, we can now make this translation back to the data science terms. Because we know now from the business perspective, all we care is to understand whether this experimental version of the product is performing better or not. But then this means that we need to conduct an A/B test, and we need to understand whether the ideas that we got and the speculation that the enroll now more general button as a call to action will be better than the secure free trial version, whether this is actually true or not from the customer's perspective. Because if we want to call us a data-driven company, we cannot just base our conclusions and our decisions for our products or for just in general for our product roadmap based on intuition or logic. We want this to be data-driven, which means that the customers are at the first place. We are customer-driven, and our customers need to tell us whether the new button is better or not. And here we have conducted an A/B test. And here I won't be using the real data. I will be using the proxy data or simulated data that I generated myself. And this one contains the similar structure and the same idea of the data that we got when we were conducting our A/B test and collecting this data. And what is our business hypothesis? In our business hypothesis, we can say that we have at least 10% increase in our click-through rate, so 10% higher engagement when we have our enroll now versus the secure free trial version of the product. So this is our business hypothesis, which means that our enroll now CTR, so click-through rate of the enroll now button, will result in at least 10% higher CTR than the secure free trial. So there exists 10%, at least 10% difference in terms of the engagement when we compare this new version of the product versus the old version of this new button. And when we translate this back to a statistical hypothesis, we can say that under the null hypothesis, we are saying that there is no statistically significant difference between the control P and then P experimental, which means the click-through rate for control group versus experimental group. So under H null, the null hypothesis, we are stating what we ideally want to reject. We are saying there is no difference between the experimental and control group CTR. And under the alternative hypothesis, so the H1, we are saying no, we do have a difference, which means that the control group's CTR is different from the experimental's group CTR. And one key part here is to mention that They are not just different, but they are statistically significantly different. So when it comes to starting the case study, first things first is to load the libraries. In this case study, we are going to use the NumPy. We are going to use the pandas as usual. For any sorts of data analytics, data science case studies, you always need those two usually. Pandas will be needed for our data wrangling, to load the data, process the data, visualize it. NumPy will be used to work with different arrays and part of the data. Then we are going to use the scipy.stats model, and from that we will import the norm function. Later on, we will see that we are using this in order to visualize this rejection region that we get from for our test to understand whether we need to reject our null hypothesis or not. And then in this case study, we also want to visualize our results and visualize our data, for which we are going to need our visualization libraries from Python, which are the Seaborn and the Matplotlib. Let's look into our data. So what we have in our data, we have 4 different columns, and of course this is a filtered data that contains the information that we need. But in general, you can have a larger database, you can have more sorts of matrices and different other metrics. But for conducting your A/B test, the pure A/B test, you actually need only the following information. So you need your user ID to understand what are the user you are dealing with. So it's the user 1, user 2, user 10. It can be that you have other way of referring to your users, and those can be, for instance, these long strings that we use to refer to our user. But given that our case is a simple one, our case study, we have just a user ID, and this user ID is just integers that go from 1 till until the end of our data. And here we got in total 20,000 users. Therefore, this number, user ID, goes to 20,000. And those 20,000 are all part of the user group, which means that they are all users and they contain both the experimental and control users. Then we have our click variable, and this click variable is a binary variable which can be either 1 or 0, where 1 refers that the user has clicked on the button and 0 means the user didn't click on the button. This is our primary metric for our A/B test. Then we have the group reference, which is this string variable, and this string variable helps us to understand whether the user comes from the experimental group or from the control group. So this can contain only 2 different values, 2 strings, and it is exp referring to the experimental and control referring to the control group. If you can see here, we got just these 3 letters, exp referring to the experimental group. And then if we go in here, because we have first the experimental and then the control ones, you can see that here we got the control group. Then we have also some timestamp, which is not something relevant, so we'll be skipping that for now. Given that this data that we have here, it's not the actual data, our data, but it's a synthetic one, but similar in terms of its structures, in terms of the nature of variables, and you can implement exactly the same steps when you have your data and you are getting it from your A/B test, and then you are conducting your A/B test case study. So in here, what we are going to make use of the most is our click variable and the group variable, because we want to find out per group what are the users that have clicked on the button. And to be more specific, we are looking for these averages. So we are not so much interested that that specific user from that specific group has clicked on the product or not. That's something that we can explore later. But for now, we are interested on the more high level. So what is this percentages? What is the click probability or click-through rate per group? And here we got groups of experimental and control, as it should be in any sort of A/B test. So once we have conducted our A/B test, then I will also provide you more insights on what you can do with your data, especially with this user ID, to learn more about the idea behind these different decisions, or whether your A/B test is different per group. But the idea is that this A/B test that we are conducting, by following all these steps and by ensuring that the pitfalls are avoided, that we are making a decision that represents the entire population. So we are using a sample that is large enough for us to make a decision for our product and for our business that will be generalized and will be a representation and representative when we apply this decision on our population. So let me close this part because we no longer need this, and let's go ahead and load this data. So here I'm using the pandas library and the common abbreviation of PD, and I'm saying pd.read_csv, and then I'm here referring to the name of the data that contains my click data. And here you can see that that data is here. So ab_test_click_data.csv. And I will be providing you this data because you won't have this in your own Google Colab. You will have the link to this Google Colab, and I'll provide you also the data such that you can put that data, you can download it first from my source and then load it in here by using this specific button in here. And by doing that, you can then go to that specific folder where you downloaded the data, and then you will have also this corresponding CSV file in your folders. So once you have that, then you will smoothly run this code. And here I'm loading that data. I'm putting under the name of df_ab_test. So basically the data frame containing my A/B test click data. What I want you to do is to showcase you how the data looks like. So here you will see the header. Given that here I haven't provided any argument, it just looks at the top 5 elements, so the top 5 rows. And here I got only the first 5 users from the experimental group. I see that some of them have clicked, some of them didn't click, and the corresponding user ID and the timestamp that they done the click action. Then when we look at the describe function, you can see here that this gives us more general idea of what the data contains, not so much what the top 5 rows just look like, which is great in terms of to understand what kind of data you are dealing with what kind of variable you have. Now you can see more the total picture, so high-level picture of what kind of data, what amount of data you got. So the descriptive statistics. So here we can see that in total we got 20,000 of users included in this data. So 20,000 observations and 20k rows. And then we have the mean. For the user ID, of course, it's not relevant. The mean is 10,000. And this is an interesting number. So we see that the average click when we look at both user and control, the experimental and control groups, it is 40%, so 0.40.52. So 40.52%. However, this is not what we are too much interested. So this is not to be confused with the click-through rate per group. What we are interested is the click-through rate or the mean click-through when it comes to the experimental group and the control group. So then we have our standard deviation. We see a high standard deviation, which is understandable given that we have this large variation in our data. We got a control group and experimental group, and this variation shows that we have a huge difference in these different values when it comes to the click event. And then we have the mean and the maximum, which doesn't give us too much information because the click event, so the click variable is a binary variable. It contains the zeros and ones. So naturally, the minimum will be the value 0 because the click can take value 0 and 1. And the largest one is, of course, 1, which means the maximum would be 1. And then for the rest, the 25%, so the first quantile, the second quantile, the 15%, which is also the median, or the third quantile, the 75th percentile, is not that much relevant. So when it comes to the descriptive statistics for this kind of data, especially if it's filtered, it's not super relevant. But if you would have a larger data, more matrices beside of click, which is your primary metric, but you have also measured some other metrics, which is recommendable, then you would see more values, which would be interesting to look at. So not only to look at the click rate, but also to look at, for instance, the mean or maybe the median of conversion rate, or the mean amount of time, the average amount of time the user has spent on your landing page, or how much time did that user end up spending before making that decision of a click. Those can be all very interesting metrics to look into from the product data science perspective, to understand the decision process and the channel and the funnel of these clicks. But for now, for our case study, what we are purely interested is in our primary metric, which is the click event. So what we can also see in here is that we got in our group, when it comes to the control group, we got 1,989 users out of all control users that end up clicking, versus the experimental group, where we have 6,116 users who did click. So do not confuse this with the total amount of users per group. This amount is the grouping of the data. So using the group by and then group. So we are grouping that data per group, and we want to see per group what is the sum of this variable, sum of the clicks. And given that the click is a binary variable, we know from basics of Python that we are basically counting the number of click events. Because if you got a binary variable containing zeros and ones, if you do the sum of the clicks, adding the zeros doesn't have any impact, which means that you end up just summing up all the ones to each other, and then you end up getting the number of, or the total amount of cases when this click variable is equal to 1. So in this case, when there is a click event. Therefore, we can see that per experimental group, we got 6,116 users out of all the experimental users that end up clicking. And then out of control group, this amount is much lower. So we end up having only 989 users clicking. So let's now go ahead and visualize this data. I want to showcase in a bar chart using these clicks, what is the total number of clicks. So I want to show the distribution of the clicks when it comes to the click event per group. And here I want to see next to each other the experimental group and control group. And as you can see here we are getting our bar charts, and the yellow corresponds to the no, which means that there was no click, versus the black corresponds to the yes, which means there was a click. So whenever you see this amount, it means that that amount corresponds to no click, no engagement from the user side. And this is per group. So this is what we are referring as a click distribution in our data, in our experimental and control groups. And the way that I generated this bar chart is by first creating this list that will contain the colors that I want to assign to each of my groups. And I'm saying 0 corresponds to the yellow and 1 corresponds to black, which means that if my variable contains an amount of 0, in this case my click is equal to 0, it means that I don't have a click, so it's a no. And this I want to visualize by yellow. Otherwise, I have a black, which means that the 1 corresponds to the case when we have click, and in this case, we will get a black. As you can see here, the yes, which means a click is visualized by this black color. And then what I'm doing is that I'm initializing this figure size by saying that I want to have a figure size of 10 and 6. You can also skip it, but I think it's always great to put the size of a figure to ensure that you are getting the size like you want it to be, such that later on you can also download or take a screenshot. Then we have this, here I'm using, as you can see, a combination of the matplotlib.pyplot library as well as the Seaborn, because Seaborn has much nicer colors. And here I'm saying we are going to make use of the Seaborn to create count plot, because we are going to count and we are going to showcase the counts per group. What is the number or the count of the clicks versus no clicks for a group called experimental, and what is the number of or the percentage of clicks versus no clicks when it comes to the group control. And then here I'm specifying that the hue should be on the click, which means that we are looking at the click variable, and we are going to use the data DF-AB test, which means that we are going to look in this data. From here, we are going to select this specific variable called click, and we are going to use this in order to group our data based on this group. So you can see that we are doing the grouping on the variable called group. So the argument is called x is equal to group. We are grouping our DF-AB test data on this group, and we are going to do the count in our count plot based on this variable click. Basically, what I'm saying here is that go and group our data DF-AB test based on group, which means that we will group based on experimental versus control. And then I'm saying go and count the click events. Count per group, so per experimental, per control group. What is the number of times when we have a no, so we have a 0, and what is the number of times when we have a yes, or we have a 1 as a value for click variable. And then as a palette, I'm using my custom palette that I just created, which should be in the form of a list, as you can see in here. If I would have here also my third group or fourth group, then I of course need to extend this color palette, because I need to have the same amount of colors as the number of groups per my target variable. In this case, the click has only 2 possible values, 0 and 1, which means that I'm only specifying these 2 colors in my list. So then we have the title of our plot, always nice to add by, and then we have our labels, which means that I want to emphasize as my X label. So here I want to have my group. You can see here is my group, because I will either have group experimental or control. That's my variable on my X axis. And on my y-axis, of course, I have the count. So I'm counting the number of times I got the no-click versus click event. So here note that the y-axis is in terms of this count. So here you can see it's 8,000, here 7,000 or 6,000, 5,000, which means that we are talking about the numbers and the counts rather than percentages. And this is important because another thing that I'm also doing is that I'm going the extra mile, and I'm also adding, beside of this counts, on the top of each bar, I want to visualize and clarify what are the corresponding percentages. It's always great to enhance your data visualization with some percentages. Percentages is easier for the person who follows your presentation to understand. For instance, if you got an experimental group and the user says here 6,000 and 4,000, they might not quickly understand that you got, for instance, in total 10,000 of users, and then 6,000 has then clicked, and then 4,000 didn't click. So then the idea is that by adding these percentages, we can then see that 61.2% has clicked in this experimental group, and 38.8% has not clicked. Of course, this is simulated data. I have specifically picked the extreme in such a way that we can clearly see this difference in the click-through rates. But in the reality, you can have a click-through rate of 10% up to 14%, which is usually a good number. If you have a click-through rate of 40%, it's great. But it really depends on underlying user base, what kind of product you got, how large is your user base. Because if you have a very large user base, then 10% can be a good click-through rate, versus if you have a very small user base, maybe 61% is considered good or average. So in here, we have just a simulated data, of course, and I've added these percentages by using the following code. So I won't go too much into detailing here. Feel free to check and see, and if something doesn't make sense, go back to our Python for Data Science course that contains a lot of information on the basics in Python. But here, just quickly, what I'm doing is that I am calculating the percentages and I'm annotating the bars. So I want to know what are these percentages, which means that per group, I want to take the total amount of clicks. I want to understand what is the number of click event when the click variable is equal to 1. So, and what are the number of cases when there was no click from the user side, which is what are the number of cases when the click variable is equal to 0. And then I'm counting those amounts and then using the total amount to calculate the percentage. For instance, in this specific case, I'm filtering the data for experimental group. I'm looking at the total number of users for this group, which is 10K. And then I'm counting the number of times when out of this 10,000 users, the amount of users that end up clicking on that button, which is the click is equal to 1 case. And then I'm taking that number, dividing it to the total number of users for this experimental group, multiplying by 100 in order to get that in percentages. And this is the calculation that you can see in here. One thing that is important here is that here I'm using this percentage. So for the current bar, I'm saying as a way to identify whether we are dealing with experimental or control group is by looking into this P, and this P in here is basically the patches. So in this case, I'm basically saying if I'm dealing with the experimental group, then go ahead and calculate what is this total amount of observations, and then take what is the number of clicks, and then divide these two numbers, multiply this with 100, and this will then give us the percentage. And then I'm doing this for each of those groups. So I'm doing it for this group, I'm doing for this group, and for this one, and for this one. So I got 2 groups, but then within each group I got clicks and no clicks. And I'm calculating this 4 different percentages, and then I'm adding these percentages on the top of those bars. So I not only want to have numbers represented in my visualizations, but I also want to add these corresponding percentages at the top, just for visualization purposes. I wanted to put this out there because this can help your data visualization toolkit, and it also will make your audience from your presentations be more thankful to you when you are telling the story of your data. So this is about the data that we have. We see that 38.8% of our experimental group users have not clicked on the button versus the 61.2% have clicked on the button based on the simulated data. And then in the control group, we have quite the opposite situation. We got the majority of the users, 80.1%, not clicking on the button versus the remaining 19.9% have actually clicked on that button. So we got a huge difference, a dissonance when it comes to the experimental group and control group. This kind of gives us an indication, hey, something is going on here. We kind of have already higher level intuition what the remaining analysis will look like, which is that there most likely will be a difference in their CTRs when it comes to the control versus experimental group and the corresponding buttons. But hey, let's continue. That's the entire goal behind A/B testing, is to ensure that our intuition, our conclusions are all based on the data rather than on our intuition. So what are the parameters that I'm using here? For conducting our A/B test, when I was designing this A/B test, the first step was to, of course, do all these different translations that we learned as part of our A/B test course, conducting it properly, which means coming up with these 3 different parameters when doing our power analysis. And usually this should be done when you are collaborating also with your colleagues and with your product managers or your product people, domain experts, because they have a lot of information on what it means to have thresholds that you need to pass in order to say that, for instance, this new version of your feature is different and is considerably different from the existing one. And here, in order for us to understand this and make these conclusions, we need to come up with these 3 different parameters that can help us to properly conduct an A/B test, as we learned when we were looking into designing a proper A/B test. So first we have our significance level. The significance level, or the alpha, the Greek letter that we are using to refer to the significance level, which is also the probability of the type 1 error. And that amount we have chosen following the industry standard, which is 5%. Given that we didn't have any previous information or specific reason to choose a different significance level, so lower or higher, we decided to go with the industry standard, which is the 5%. This means that we want to compare our p-value of our statistical test to this 5% and then say whether we have a statistically significant difference between the control and experimental group based on this 5% significance level. And let's refresh our memory on this alpha. This alpha or significance level is also the probability of type 1 error. So this is the amount of error that we are comfortable making when we reject the null hypothesis, while the null hypothesis is actually true, which means that we are detecting a difference between the experimental and control version while there is no difference. And we are making that mistake. And here we are saying that we are fine and we are comfortable with making this mistake at a maximum of 5%. But higher than that, it's not allowed. We are not comfortable making error higher than 5%. Then the next variable, in this case, the B or beta, the probability of type 2 error, which is the opposite of the type 1 error, which is a false negative rate, or the amount of time, the a proportion of time when we end up failing to reject the null hypothesis, while null hypothesis is false and it should have been rejected. Then the 1 minus beta is actually power of the test. So what is the amount of time we are correctly rejecting our null hypothesis and correctly stating that there is indeed a statistically significant difference between our experimental group and our control group. So we have chosen for this the industry standard as well, which is the 80%. But given that for your results analysis, in this case, for conducting this case study, that part of the power analysis is not relevant. We use that when calculating our minimum sample size, but we don't need that when conducting our results analysis. Therefore, I'm not initializing that as part of this code. So here I'm only providing to my program the values for my significance level, which is 0.05, or this is the same as 5%. And then the delta, which is the third parameter, and this delta is our minimum detectable effect. So this Greek letter delta, which is the minimum detectable effect, helps us to understand whether, beside of having this statistically significant difference, whether this difference is large enough for us to say that we are comfortable making that business decision to launch this new button. So it can be that when we are conducting an A/B test, we are finding out that the experimental group has indeed higher engagement than the control group. And we are getting a small p, or at least smaller than the alpha, and we're seeing that p is more than the alpha level, which means that we can reject the null hypothesis, and we can say that the CTR, or the click-through rate of the experimental group, is statistically significantly different from the control group at 5% significance level. But we know from the theory of A/B tests that only that is not enough. Only statistical significance is not enough for the business to make that important decision to launch an algorithm or to launch a feature, in this case, to change our landing page, the button, from the Start Free Trial to the Enroll Now. Which means that we want to have enough users and we want to have enough difference, large difference in our click-through rate, so enough users saying that we are more happy with this new version of the landing page for us to go and change our feature. And what is this definition of enough? What is the difference in the click-through rate that we need to detect after we have detected the statistical significance in order for us to say that we also have a practical significance. So practically, we are also comfortable making that business decision and then launching this new feature and changing our landing page button. And that is exactly what we have under our delta, this minimum detectable effect. In this case, we have chosen for delta of 10%. So you can see here 0.5. This is 10%. This means that our delta, or the MDE, the minimum detectable effect, is 10%. This means that we are saying not only we should have a statistically significant difference between the experimental group and control group, but also we need to have this difference to be at least 10%, which means that we need to have detected that the experimental version of the landing page results in at least 10% higher click-through rate compared to the control version for us to go ahead and to launch this new version and deploy this new UX feature. So this is really important because many people go and check for statistical significance. So they do their alpha and then check whether the p-value is more the alpha and then say, hey, we have a statistically significant difference. And then they are done with that. But that's not correct. After you have conducted your statistical significant analysis and you have detected that your experimental version has a statistically significant different CTR than the control version at your alpha significance level, the next thing you need to do is to ensure that you also have a practical significance beside of this statistical significance. And this practical significance you can detect and you can check when you use your MDE or your delta and you compare it to your confidence interval that you have calculated. Something that we have also learned as part of the theory of conducting a proper A/B test. But once we come to that point, so after we check for our statistical significance, I will also explain how exactly we will need to do this check. And at the same time, we will also be refreshing our theory on the practical significance. So let's now go ahead and calculate the total number of clicks per group by summing up these clicks. And I also want to calculate and group by this amount just to showcase how you can do that on your own. So here what I'm doing is that I'm taking my A/B test data, I'm grouping by group. Group is the variable that contains the reference whether we are dealing with experimental group or control group. And as you know from our Python series and demos, Python for Data Science course, that whenever we want to group that data, a pandas data frame, first we need to say pandas data frame name dot group by, within parentheses the variable that we are using to do the grouping, which is in this case group, and then within square braces I want to emphasize and put the name of a variable that I want to apply operations on. So I want to group my data on the group variable and I want to count the number of times I have a click in my control group and in my experimental group. This will be my X control and X experimental variables. So X control will then contain information about number of clicks in my control group, and then X experimental will contain the number of clicks in my experimental group. And given that I want to refer to the name of that group after I did my grouping, so I am getting this shape of data frame. Of course, I then need to use my .log function in order to properly call that amount. So to understand what is this amount corresponding to this index and what is this amount corresponding to this index. And given that my index is in strings, I'm then using here my .log function, something that we also learned as part of our Python for Data Science course. So here is basically the printing, just writing nicely what are the results, which means that we are counting that let me count again, that the number of clicks for my control group is 1,989. So you can see that it is. Want to double check and see what we got. Yes, so we got the same number, so we are dealing with the same data set just to make sure. And here the number of clicks for our experimental group is equal to 6K and then 116, so 6,116 clicks. So then we are calculating the pooled estimates for the clicks per group. Let me quickly fix this typo. So calculating the pooled estimate for the clicks pair group, which means the pooled estimate for the experimental group and for the control group. So let me quickly add here how I can calculate the total cases when we got experimental group users. So what is the number of users in the experimental group and what is the number of users in the control group. So here what I want to do is that I want to say that the group, the DF test group, should be equal to experimental, and this of course should be my filter, and I want to count this. And let me quickly copy this. I saw that it's already under the control, so here I'm changing to the control, and this will need to give me the number of users in each of these groups too. So number of users in control and number of users in click, and here I will simply check this. So I will print then the number of users per group, and at the same time I will also click the number of clicks per group. There we go. So now when we have done this, what we are ready to do is to go ahead and calculate the pooled estimate for clicks per group, which means per control group and per experimental group. For that, what we need to do is to take the number of clicks of the control group, divide to the number of all users for control group, as you can see in here, x control divided to n control, and we are referring to this variable as p control head, because we know that the estimate of this click probability is always with a head. It's just the way that we reference it in statistics and in A/B testing. So this is the estimate, something that we are estimating, therefore we are saying head. And then we have the same for experimental group, which means that the estimate of the experimental group's click probability is equal to xexp and then divided to nexp. Then, in order to calculate the pooled estimate or pooled click probability, which means the value that will describe both the control group and experimental group, we need to follow this formula, which means that we are taking the x control, we are adding to that x control the x experimental. This is our nominator of our value. And then we are dividing this to the sum of the sizes of each of those groups, which is n control and n experimental. So this is the common formula of the pooled estimate when it comes to this type of experimentation, when you are dealing with primary metric that is in the form of zeros and ones. And if you want to refresh your memory on this type of formulas, then make sure to also check our A/B testing course, because in there we go in detail in this specific lesson of the A/B test results analysis. We are looking into this all these formulas on how we can calculate the pooled estimate of this click probability. So click probability, but then we are calling it pooled click probability, and then what we got is this value. So that amount is then 0.40. This number should look familiar because this is then the mean that we saw when we were looking at the descriptive statistics table. If you can recall this table, let me see this number. So now basically we are then calculating this manually because we need a variable that will hold this value. So it is simply summing up all the clicks for control group and experimental group to get the total number of clicks, and we're dividing it to the total number of users. So n control plus n experimental. So now when we have this, we are ready to also calculate what we are referring as a pooled variance, also something that we have learned as part of the theory for A/B testing. So the pooled variance is equal to the pooled estimate of the clicks. So P pooled head, something that we just calculated, multiplied by 1 minus P pooled head. So the click event, the estimate of the click probability multiplied by the estimate of no click And we know already this idea of Bernoulli distribution, that the variable that describes this process of clicks and no clicks follows kind of this idea of Bernoulli distribution when we have a click and no click. So we have probability of click, and then we have a probability of no click, which is the one minus that click probability. So that's the idea, or the part of the formula that we are following as kind of an intuition. And then this multiplied by 1 divided to n control plus 1 divided to n experimental. So here I'm purely following the formula for the pooled variance. If you want more details and explanations, ensure to check the corresponding theory lecture, because we are going into details of each of those formulas and understanding why we calculate this pooled variance and pooled estimates in this specific way and using these specific formulas. So here, by just following the formula, I'm getting that the pooled variance is this amount. So this is in a nutshell how I calculated my pooled click probability and the pooled variance of that click event. And we are going to need that in the next very important step, which is calculating the standard error and calculating the test statistics. Because in this case, what we are doing is that we are dealing with a case when the primary metric is in the form of zeros and ones. So let's now quickly talk about the choice of a statistical test before conducting the actual calculation of standard error and the test statistics. So here I went for the 2 samples that test, and let me explain you why and what is the motivation. Because as we learned as part of the theory, whenever we have a primary metric that is in the form of an averages, like we have now, because we are using the p-control head and p-experimental head, so we have a primary metric that is the click-through rate, which is the average clicks per group. So we have calculated the average click per experimental group and per control group. Then the primary metric, the form of it already dictates, given that it's in averages, that we need to look at either parametric tests corresponding to these averages or non-parametric tests corresponding to the averages. In this case, I went for the parametric case because it has better properties if I have this information about the distribution of my data. And why do I have this information? And then this also dictates the choice of my statistical test. Well, I have a size of my sample which is over 100 and actually over 30. That's the threshold that we tend to use in statistics and in A/B testing in order to say whether we have a large size or large data or not. If our sample is not large, so it contains less than 30 users per group, which happens as well, then we say that we need to go for statistical tests that will be specific for this kind of cases, because we can no longer make use of the statistical theorems like the central limit theorem, which helps us to take the inference, so to make use of the inferential statistics and make conclusions regarding the distribution of our population just having the sample. And what do I mean by that? So if my sample is larger than 30, like in this specific case, I got 10,000 users per group, so it is definitely larger than 30 users. Then in that case, I can say that by making use of the central limit theorem, I can say that my sampling distribution is normally distributed. And this is simply making use of the central limit theorem, something that we have also learned when we were looking into this concept of inferential statistics as part of the Fundamentals to Statistics course in LunarTech. So this is a powerful theorem that we use in A/B testing in order to make our life easier, because when we have a sample that is larger than 30 for each of these groups, then we can say that even if we don't know the actual distribution or the name of the distribution that our sample follows when it comes to the click event, so the random variable that describes this number of clicks or the average click-through rate, what is that distribution exactly? But given that we have that this size is large enough, it's larger than 30 users, we can say that by making use of the central limit theorem, we can say that the sample distribution follows a normal distribution, if given that the sample size is large enough. And this helps us to say that, well, in that case, it doesn't matter whether we make use of the two-sample z-test or two-sample t-test. We can make use of either of these tests in order to conduct our analysis. And we had this specific template to make this choice easier in our A/B test course at LunarTech, where we were making all these decisions and saying, if the sample size is this, we need to do this. If the sample size is this, we need to do this. And in this specific case, following that exact structured and organized approach, I ended up saying that my sample size is large, so it's larger than 30, so I can then make use of the central limit theorem. I then know what is the random, what my random variable describing this click-through rate follows the kind of distribution, in this case, a normal distribution. And then this means that whether I use a t-test or z-test doesn't really matter. I'm going to end up with the same conclusions. Therefore, I will just go with the two-sample z-test, simply because it is just easier for me to do, for example. You can also go with the two-sample t-test, and you can even change this case study and tweak it, and then make it your own and put it on your resume in that way by making it more unique. And that will be totally fine, because you will see that you are going to end up with exactly the same conclusions as we do in this specific case study. Because if you have a large enough sample, it won't matter whether you have a two-sample z-test as your parametric test or the two-sample t-test. And if you want to know why this matters and all these different detailed statistical insights, make sure to check the actual course dedicated to A/B testing, because there we cover this all, and you will then become a master in the field of A/B testing. Now we know these decisions and the motivation behind choosing the two-sample z-test. Let's now go ahead and do the actual calculations. So here we have a standard error, which we calculate by taking the pooled variance and taking the square root of it. And this is again using the idea of these formulas that we learned as part of the A/B test. So we are using this pooled variance, taking the square root of this, which gives us the standard error. And the standard error, as you can see in here, is then equal to 0.0069299499, this amount. Then we calculate our test statistic for our two-sample z-test. So the test statistic is equal to p control hat minus p experimental hat divided to standard error. So here you can now see the motivation behind not only computing the p pooled hat, but really also the p control hat and p experimental hat. And then I take the p control hat and subtract the p experimental hat, and I divide it to the standard error to compute my test statistics. Once I did this, as you can see, this is this amount. So test statistics for our two-sample z-test is this amount minus 59.56 rounded. Then we can also compute the critical value of our z-test, which is by using this norm function that we loaded in here from the SciPy. And this will help us to understand what is this value from our normal distribution table, the standard normal distribution table, where by making use of this table, we identify what is this critical value that we need to have to create our rejection regions and to say whether we can reject our null hypothesis or not. So to conduct our test, we need to have a critical value to which we will compare our test statistics. And this critical value will be based simply on the standard normal distribution. So this is this norm.ppf. And then probability function, basically. The probability function that comes from the normal distribution, standard normal distribution. And as you can see, this corresponds specifically to this percent point function, which is the inverse of the cumulative distribution function. So this based on the alpha divided 2. So 1 minus alpha divided 2 is the argument that we need to put for our percent point probability function. And why divided to 2? Because we have a two-sample test. So because we have a two-sided two-sample test, sorry. So if you want to understand this difference between two-sample test, two-sided test, please check out the Fundamentals to Statistics course at LunarTech, because we cover this topic in detail, and it's a very involved topic. It contains many complexities from statistical point of view. So I won't be spending in this case study too much time on that. Here I'm assuming that you know this formula already, but if you don't, and if you quickly need to do your case study in A/B testing, feel free just to copy this line, which basically is a value that we need based on the corresponding chosen statistical significance level that we need to compute to compare our test statistics. So our test statistics is this value, and the value that we need to compare it to is this Z critical value. So we can see that this critical value is then equal to 1.96. This is actually a very common value that we know even without looking at a standard normal table. When you make use of this test enough often, then you know that the critical value corresponding to a two-sided test when it comes to a normal table is equal to 1.96. This is just a value that we know. And in here, by even without calculating the next step, which is the p-value, we can even say already what is the decision we need to make in terms of statistical significance. Because we know that one way we can test our hypothesis, statistical hypothesis, is by computing the test statistics and checking whether test statistics, the absolute value of it, is larger than the critical value. And we see that the test statistics is equal to minus 59.56. The absolute value of that is 59.56, and that value is much larger than our critical value, which is equal to 1.96. This already gives us an idea that we can reject our null hypothesis at 5% statistical significance level. But I want to go on to the next step, actually, because that's more structured, more organized way to doing and conducting experimentations, as in the industry, we tend to make use of the p-values instead of making use of this econometrical approach and statistical approach of testing the statistical test. So once we have calculated our test statistics, the next thing we need to do is to calculate our p-value and then use that p-value compared to the significance level alpha, and then make a decision whether we need to reject our null hypothesis and say that we have a statistical significance, or we cannot reject our null hypothesis and then we need to say that we don't have a statistical significance, so we don't have enough evidence to reject the null hypothesis. So the idea here is that we need to make use of our normal function, and specifically the norm.sf, so making use of exactly the same library, the norm from scipy.stats. And then this time we're using the survival function, which is the 1 minus the cumulative distribution function of normal distribution. This comes again from statistics. And then using the absolute value of our test statistics, multiplying it by 2, given that we have a two-sided test, I'm calculating my p-value. This is simply by making use of the same formula that we saw when we were studying the A/B test from a technical point of view, because we learned that the p-value is then the probability that Z will be smaller than equal to minus test statistics, or that the test statistic is smaller than equal to Z. So we basically want to calculate what is this probability, the p-value, which is equal to the probability that our test statistics will be smaller than the critical value, or our negative of the test statistics will be larger than equal of the critical value. And we want to know this probability, because what this probability represents is that what is the chance that we will get a large test statistics? Well, this is due to a random chance and not because we have actual statistical difference between the click-through rate of the experimental group versus control group. So this is the idea behind p-value. So what is this chance that we are mistaking this random mistake, this random observation that we got a large test statistic, and saying that there is a statistical significance? Well, there is no such thing. And we are purely getting this large test statistics because of the random chance. If the probability of getting a large test statistics by random chance is small, so if this p-value is small, then we can say that we have a statistical significance. That's the idea behind it. And this p-value, when we calculate, we are storing it in this variable called p_value. And then the next thing what I'm doing is that I'm writing this function called is statistically significant, which takes arguments as p-value and alpha. So I just need the p-value that I just calculated for my test statistics. And then I want the statistical significance level that I want to use for my test. And then this is the value that comes from my power analysis. As I mentioned before, that's the 5%. This p-value I'm calculating for my test statistics. So in here, and then I'm taking the two and I want to compare them. So I want to assess whether I have a statistical significance by comparing my p-value to my statistical significance level alpha. And what is this comparison? Well, we know from the theory that if we have a low p-value, and specifically in the p that we are getting, the p-value is more than equal the 5% or 0.05, which is the significance level, then this indicates that we have a strong statistical evidence that the null hypothesis is false and we need to reject it. So we have a strong evidence against the null hypothesis. And otherwise, if the p-value is larger than 0.05, so it's larger than 5%, that we have chosen as the maximum threshold of that mistake, so the significance level is no longer the largest element, but the p-value is larger than your significance level, then this indicates that you don't have enough evidence against the null hypothesis. So your evidence is weak. This means that you fail to reject the null hypothesis. So this is what I'm doing in here with this code. So I'm saying print the p-value first, and we are rounding it up with this round function. I'm rounding it to the 3 decimal. And then I want to check and determine whether I have a statistically significance or not. And the way that I'm doing that is I'm saying if my p-value is more than my alpha, or actually let's add smaller than equal than alpha, then we can print that there is a statistical significance, which indicates that the observed differences between the experimental and control groups are unlikely to occur due to random chance, which means that this is not random chance, and we have a strong evidence that there is a statistical significance. And this suggests that this new feature that we got, this new version of our landing page with this call to action as the enroll now, is better and results in higher, statistically significantly higher click-through rate than the existing version of the control group. So there is a real effect. Then otherwise, if this is not the case, which means that my p-value is larger than my alpha, then I'm saying print that there is no statistical significance and that the observed difference that we see in the click-through rate is not because of the real difference in the performance, but truly this is just a random chance. So here we can see that once we run our, we call the function in here, which is simply the function name and the argument. So p-value and alpha. Alpha comes from the initialized value that we had from our power analysis. So from here, we initialize this value, it's 0.05. And then here, we got the p-value that we just calculated. Then what we are getting in here is that our p-value is actually so small that it's rounded to the 0. So what this means is that there is evidence that suggests that at 5% statistical level, significance level, that the click-through rate of the experimental group is different from the click-through rate of the control group. Note that I'm not saying higher or lower because our statistical test was two-sided. So under null hypothesis, we had that the P control, so in here, as you can see, our P control was equal to P experimental, and under the alternative, we had that the P control is not equal to P experimental. This means that we have now rejected the null hypothesis. We have found evidence that suggests that the null hypothesis can be rejected since our p-value is 0 and is smaller than the statistical significance level 5%. And this means that we can reject the H-null, and we can say that there is enough evidence to say that p-control is not equal to p-experimental. And given that we saw from the visualizations and from our calculations that the click-through rate for our experimental group is much higher than the click-through rate of the control group, we can also say that we have found evidence that at 5% significance level, we have found out that there is a statistically significant difference between the experimental and control group's click-through rate, and that the experimental group's click-through rate is actually higher, so statistically significantly higher than the control version's click-through rate. So this is really important because this suggests that this difference in their click-through rate is not due to random chance alone, but truly that there is evidence, statistical evidence, that can support this hypothesis that there is a true difference between the performance of the experimental version of the product, so in this case, in our case, the landing page that has Enroll Now button, versus the control version of the product which had the start free trial version of the landing page, the existing version. So beside of calculating this p-value, it's always a great practice to also visualize your results. And this is great for your audience who are technically sound and who know these different concepts, and you want to visualize the results that you got, not only by showing some number that is a p-value and say, hey, I have a statistical significance, but you also want to showcase the actual picture of what you got, what is your test statistic, what is the significance level that you use to kind of tell a story around your numbers. And that's the art behind the data science, I would say. So let's go ahead and do some art. So what I'm doing here is that I am making use of my standard normal distribution, or the Gaussian distribution, the way that we are referring to the standard normal distribution in statistics. I'm saying that my mean, or the mu, is equal to 0, my sigma is equal to 1, which is my standard deviation, and I'm saying that my I want to now plot my standard normal distribution by getting my x values, which are the number of x elements that I want to have my x-axis, and then taking the PDF, or the probability distribution function, for the normal distribution by using the SciPy library. I'm then providing my x values for which I want to get my corresponding values of y. So basically, here are all the values between, let's say, minus something, minus 3, and then so between minus 3 and 3. And I want to find all the y's corresponding to this, which basically plots the probability distribution function of the Gaussian distribution or the standard normal distribution. And then I want to add to this graph also the corresponding rejection region. And as you can see, it is here. So then what I'm adding here by using this part of the plot is that I want to fill in the rejection regions. So I'm saying, for all the values in this figure, whenever the value is lower than that threshold, in this case the threshold is the Z critical, 1.96. So whenever my threshold is smaller than minus this 1.96 and larger than this 1.96, then we are in the rejection region. We are saying then, if my test statistics is falling in the rejection region, in this case you can see that we are in the far left, so the test statistic is minus 59.44, and it's much lower than this threshold, as you can see in here. This is this left blue line in here. Then in this case, it falls in this rejection region. So actually this entire thing is the rejection region. it starts from here and it goes all the way to here. Anything in this region means that we have a test statistic falling in the rejection region, which means that we can reject the null hypothesis. If we were to get a test statistic that is very large and very positive, it means we would be in this part of the figure and again in the rejection region. Anything above this line is then going under this category of rejection region, and also anything in here. So for anything in here, we are in the rejection region. Being in the rejection region, it means that we can reject the null hypothesis and we can say that we have a statistically significant results. So now when we have our statistical significance, it's always a great idea to go on to the next step. And it's actually mandatory to do this because not only a statistical significance is important, but also the practical significance, as I mentioned in the beginning of this case study. So for that, what we are going to do is first we are going to calculate the confidence interval of the test. And this confidence interval will help us to, first of all, make comments regarding the quality of our test and its generalizability at our entire population and the accuracy of our results. And then we will use this confidence interval to make comments and to test for the practical significance in our A/B test. So let's go ahead and calculate the confidence interval. So as we learned as part of our lectures, the confidence interval can be calculated by first taking the p-experimental head and p-control head and the standard error and the z-critical. So here we need these two different estimates of the experimental group's click-through rate and the control group's click-through rate. We also need the standard error of our two-sample z-test as well as the critical value. And then we need to first calculate the lower bound of our confidence interval, and then we need to calculate the upper bound of our confidence interval. And in this case, given that the statistical significance level we are using is alpha, the z-critical is based on that. Therefore, we are also saying that we are calculating the 95% confidence interval. So in here, the way we will calculate the lower bound is by taking the p-experimental head, subtracting from that the p-control head, and then once we have done that, we then subtract from that the standard error multiplied by z-critical value. And we are just rounding this up to the 3 decimal behind the 0. Then we are doing the same thing only with a plus sign in here for the upper bound calculation of the confidence interval. So this is just pure following the formula of the confidence interval that I will set you here. And let's go ahead and print this value, which is this interval. So what we are seeing here is that we have a confidence interval that is from 0.399, so 0.4 to 0.43. So quite a narrow confidence interval, I would say, which is actually a good sign because this confidence interval that provides this range of values within which the true difference between this control and experimental group's proportions or the click-through rate is likely to lie within a certain level of confidence, in this case 95% confidence. This is very narrow. And if it's a narrow confidence interval, it means that the accuracy of our results is higher. And it means that the results we are getting based on our smaller sample, it will most likely generalize well when we apply these changes and deploy these changes and we put this new product in front of the entire population of users. Because now we are doing all this experiment for a small group, for the sample, and this confidence interval that is narrow, it's not wide, it's narrow, it means that the results that we are getting are accurate, more or less accurate. And this means that the results that we are getting based on the sample are most likely a true representation of the entire population that we got. This is the idea behind the width of the confidence interval. The narrower it is, the higher is the quality of your results, which means that the more generalizable are your results. So let's now go on to the final stage of our case study, which is to test the practical significance of our results. So now when we know that the statistical significance is there, the experimental version of our feature is statistically significantly different from the control version in terms of the click-through rate. And we have seen that the confidence interval is narrow, which means that our results are accurate, with quite high accuracy. Then we can now comment on the practical significance of our results. This means we want to see whether the significant difference that we obtained, whether this difference is actually large enough from the business perspective to say that it's worth to put our engineering resources and our money and our product into to put through this change, and to say that it's worth from the business perspective to change this button and to put this into the production and in front of our users. And of course, here we are not only talking about the engineering resources that it will take from us to change this, and the deployment and the monitoring, but also in terms of the quality of the product we are providing to our users. Because whenever we are making a change to our product, it is a risk because we are changing what our user is used to see. And this can always be scary when it comes to the business, because we don't want to make our customers scared. So therefore, we need to also check for this practical significance. So for that, what I'm doing is that I'm creating this Python function that will take two arguments, so two values, that is the minimum detectable effect, and then the 95% confidence interval that I just calculated. Those will be the two arguments for my function, and I'm calling this function is practically significant. And this function will go and check whether the practical significance is there or not, and it will then return true or false, and then it will also print whether we have a practical significance or not. And we learned from the theory, and we know from this A/B testing concept, that whenever the MDE or the delta that we got, the minimum detectable effect, is larger than the lower bound of our confidence interval, it means that the lowest possible value that we can get based on the results that we obtain in our sample, that amount is smaller than the minimum detectable effect that we assumed before even conducting our A/B test. This suggests that we have a practical significance, and the difference, the minimum difference that we will obtain, is large enough for us to have a motivation to make this change in our product. For that, what I'm doing is that first I'm taking my 95% confidence interval, and I'm taking the first element, because we know that a confidence interval is actually a range, so a tuple of two numbers, the lower bound and upper bound. I need the lower bound because all I care for this practical significance is to compare the lower bound of the 95% confidence interval to this minimum detectable effect, which is my delta. So therefore, I'm taking this lower bound of confidence interval, putting that into a variable, and then I'm using this variable, this lower underscore bound underscore CI confidence interval, and I'm comparing this to my delta. I'm saying if my lower bound of the confidence interval, actually I'm noticing that here I got a mistake. It should be the other way around. We need to say that if our delta is larger or equal the lower bound of the confidence interval, which is the same as if our lower bound of the confidence interval is smaller than equal our delta. So if we can also write this the other way around. So if our delta is larger than equal than our lower underscore bound underscore CI, then we can say that we have a practical significance. So with the MDE of, in this case, so I want to use my initial delta, therefore I won't be initializing this. So you might recall here a delta of 10%. I want to still make use of that delta. So therefore I will just go ahead, and then in here, what I want to do is to call this function by using that specific delta. So I want to have a 10% as my MDE. And whenever this delta will be larger than the lower bound of my confidence interval that I just obtained, I will then say that we have a practical significance. And with an MDE of 10%, the difference between control and experimental group is also practically significant. So you can see that the lower bound is 0.04, something that we obtained here. And that amount is then compared to this delta. And here you can see that we have concluded that we also have a practical significance. So amazing. We have come to the end of this case study. And in this involved case study, we have conducted an entire A/B test result analysis. So this case study in A/B test. And to end, going from the point of loading the data and then understanding this business concept or business objective of A/B test, where we were testing whether the Enroll Now button, which is the new version, the experimental version, should replace the existing button, which is the Secure Free Trial. And based on this case study, what we found out is that we have a statistical significance at 5% significance level, suggesting that we can reject the null hypothesis, and we can say that indeed there exists a statistical significant difference between the click-through rate in the experimental group versus control group, and specifically that the Enroll Now experimental button results in statistically significantly higher click-through rate than the Secure Free Trial button. And beside this, we also checked the accuracy of our results by looking at a confidence interval, and we saw that the confidence interval was quite narrow, suggesting that the results we obtained were quite accurate. And this means that the results that we got for the sample will generalize to our population of users. And finally, we have also checked the practical significance of our results by using the 95% confidence interval and comparing the lower bound of that interval with our minimum detectable effect delta. And we saw that we will have at least 10% significant difference between the control groups CTR and the experimental group CTR, and the experimental group CTR will be at least 10% higher than the control groups. And this suggests that from the business perspective, we also have a motivation. Beside of this statistical significance, we also have practical significance, suggesting that we also have enough motivation and reason from the business perspective to put this new button into production. So we can conclude that based on this data-driven approach and conducting an A/B testing, we can see a clear motivation of deploying this new button, Enroll Now, and replace the existing one, Secure Free Trial version. And we will then expect to see more users clicking on this and engaging with our product. And for now, this will be all for this case study. If you want to learn more about A/B testing, make sure to check our A/B testing course as well as the Ultimate Data Science Bootcamp. Don't forget to try our free trial, this time using our Enroll Now button. And if you want to see more case studies like this, make sure to check our other case studies. We have many case studies also included as part of our Ultimate Data Science Bootcamp, where we go in detail of these different steps and we conduct different sorts of case studies to put our data science theory into practice, including from the field of NLP, machine learning, recommender systems, advanced analytics, and also A/B testing, and soon also from AI. So for now, thank you for staying with me and conducting this case study. Happy learning your one data point at a time.
Hi. So let's get started. Alright, let's now go over the data set we'll be using. So we are using the Superstore sales data set, and it has 9,800 rows, and the columns: order ID, order date, ship date, shipping mode, standard class, second class, or other classes, and the customer ID with them, customer name, the segment, meaning who bought the product, was it a consumer, a corporate, or a home office, and the clients mainly come from the United States, and it's also specified from which city of the United States they come from. So we shall import this to our Google Colab and start working on it. Okay, so let's now import the necessary Python libraries. We'll import pandas as PD. We'll also import numpy as MP, import matplotlib pipeline. We import seaborn as SNS. So let's also import the data frame we'll be using. Copy path. Perfect. So this is how it looked like on Kaggle, and this is also how it looked like when we have imported. So let's now look up the data frames with larger info. So everything seems to be consistent but the postal code. It seems that 11 postal codes are missing. Okay, so what we can do is to fill in those null values. Okay, so as you can see, we have replaced the null postal codes, customers that didn't have any postal code, and we have put a 0 inside it. Alright, so let's now move on to checking for duplicates. If df.duplicated.sum is bigger than 0 dash print. So let's now see if there are actually duplicates, and if there are duplicates we will print duplicates exist, and if there are not we'll print null duplicates found. Alright, so as you can see there exists no duplicate. So let's move on to customer segmentation. Let's first create a variable named types of customers, and let's extract out of our data frame called segment.
As you can see from our data frame, we have a married segment within our data. This segment includes a list of the types of customers in our data frame. We have both consumer and corporate customers. So let's get started with customer segmentation. The main problem is that many large businesses struggle to understand the contribution and importance of their various customer segments. They often lack precise information about their main buyers, relying on intuition rather than data. This leads to misallocation of resources, resulting in revenue loss and decreased customer satisfaction. For example, if your store primarily caters to consumers, it's crucial to tailor your marketing and customer satisfaction efforts to resonate with their needs and preferences. By focusing your resources on understanding and catering to your consumer base, you can avoid misallocating resources to large corporates. This ensures you're providing a satisfying customer experience for your primary demographic, ultimately leading to increased customer loyalty and revenue growth.
And we can create a pie chart or bar graph from it to clearly illustrate the revenue contribution of each customer segment. And this will allow us to tailor more of our marketing resources, our customer satisfaction resources towards.
Once you've completed customer segmentation, the next step depends on your strategic goals. Here are a few ways to proceed. Focus on your most valuable segment. If your existing customer segmentation reveals a particularly profitable segment, such as consumers, tailor your marketing, product offerings, and customer service to deepen your engagement with that group. Target new segments. If you want to attract more corporates or home offices, you'll need to understand their unique needs and pain points. Start by researching these segments. What are their challenges? What solutions would appeal to them? Develop tailored messaging and consider offering specialized products or services to attract these new customer types.
Alright, so let's get started. So this will extract the types of customers from our data frame. Perfect. So it's consumer, corporate, and home office. Those are all the variables that are in our data frame. Alright, so let's count the unique values in our segment, and we will do this by number of customers. So what this meaning does is it counts unique values in our segment and resets the index to turn them into a column. And then we can correct the renaming of columns. So we want to give our segment the name of like total customer or type of customer. I will go with the type of customer. So we will say number of customers is equal to number of customers that I'll rename, and want to call the column, which is the name segment. We want to rename it to type of customer. Now, if you want to print that, print number of customers. There are 5,101 consumers, and for corporates there are like 2,953 corporate buyers, and 1,746 home offices. And if we want to create a pie chart out of this, we can plot it by saying plot.pie, number of customers, and want to base a pie chart on the count, and want to label number of customers, total customers. Perfect. Alright, so as you can see, we had to rename it type of customer, total customer. So you can see that from this pie chart, our main consumer segment is 52%. 30% of our orders come from corporates and 18% from home offices. You can see who we have to exactly focus on, which are consumers.
While consumers hold the majority, focusing solely on them overlooks significant potential within the corporate and home office segments. Let's explore how to balance resource allocation for all three segments to maximize growth. To gain even deeper insights, we should integrate our customer data with sales figures. This analysis will help us identify which segments generate the most revenue per customer, average order value, and overall profitability, customer lifetime value. Additionally, we can segment customers by purchase frequency and basket size to understand their buying behavior within each segment. Here are some additional questions to consider for a more comprehensive analysis. Customer acquisition cost, CAC. How much does it cost to acquire a customer in each segment? Customer satisfaction. How satisfied are customers in each segment? Churn rate. What is the rate at which customers leave in each segment? By analyzing these factors alongside revenue and customer lifetime value, we can create a customer segmentation model that prioritizes segments based on their overall value and growth potential.
We can also plot a bar graph for the total sales for each customer type and group the data by the segment column and calculate the total sales for each segment. And you want to do this so right now you don't see the exact sales numbers. The bar chart, you can see the exact sales numbers for each customer type. So let's plot it. So there are around 1.2 million from our consumers, and we have around 600 or 700,000 from our corporates. We can also plot a bar graph from this, which means plotted bar sales per segment, customer type of customer, sales per segment, total sales.
This bar chart effectively illustrates the distribution of sales across our customer segments. Consumers account for the largest portion of sales, 1.2 million, followed by corporates, 1.0 million, and home offices, 0.8 million. While the chart is clear, a deeper analysis can help us optimize our marketing efforts. Customer Lifetime Value, CLTV. Calculate the CLTV of each segment to identify which segments generate the most revenue over time. This will help prioritize customer segments for marketing efforts. For example, if you find that the home office segment has a higher CLTV than the consumer segment, you may want to invest more resources in marketing campaigns targeting home office customers. Market research, conduct market research to understand the specific needs and preferences of each customer segment. This will inform the development of targeted marketing campaigns. For instance, you might discover that consumers in your data are price sensitive, while corporate customers are more interested in bulk discounts and reliable service. You can use this knowledge to tailor your marketing messages to each segment. Average order value. Analyze average order value by segment to identify opportunities to increase revenue per customer. Let's say your analysis reveals that corporate customers have a higher average order value than consumers. You could develop marketing campaigns that encourage consumers to purchase bundles or higher priced products to increase their average order value. Customer acquisition cost, CAC. How much does it cost to acquire a customer in each segment? Knowing CAC can help determine the return on investment, ROI, for marketing efforts. Here's an example. Let's say it costs $100 to acquire a new corporate customer, but only $20 to acquire a new consumer customer. If the CLTV, customer lifetime value of a corporate customer is significantly higher than the CLTV of a consumer customer, then spending $100 to acquire a corporate customer may still be profitable. However, if the CLTV of the corporate customer is only slightly higher than the CLTV of the consumer customer, you may want to focus your marketing efforts on acquiring more consumers because the cost of acquisition is much lower. Customer satisfaction. How satisfied are customers in each segment? Understanding satisfaction levels can help identify areas for improvement and reduce churn. Here's an example. You can conduct surveys or collect customer feedback to understand satisfaction levels. If you find that corporate customers are less satisfied than consumer customers, you may want to investigate the reasons for their dissatisfaction and make changes to improve their experience. This could involve improving your customer service, offering more competitive pricing for corporate customers, or developing products or services that better meet the needs of corporate customers.
We can also create a pie chart for our sales, which we can do by plotted pie, sales per segment, total sales, and we name it labels is equal to sales per segment, type of customer. 51% of our sales come from our consumers, 30% from our corporates, and 19% from home offices. Alright, so let's now move on to the customer loyalty. As a business, you want to make sure that your most loyal customers stay happy. This will make sure that those customers keep on coming back, keep on bringing new people, and also placing new orders. So you will decrease the cost on acquisition of new customers because there will be already existing customers, and you'll also be able to make sure that your revenue either stays at the same level or increases by keeping your most loyal customers happy. And you want to do that as a business. Now, we can do this by either the following ways. We can rank the most loyal customers by the amount of orders they have placed or the total they have spent.
You have analyzed your data, pinpointing your 30 most loyal customers. This represents a significant opportunity to strengthen these relationships and maximize their lifetime value. Here is a powerful approach. Design a targeted email specifically for those high-value segments. Proactively offer personalized support with inquiries such as, "How can we assist you today?" This demonstrates your commitment to their success, proactively addressing potential issues and fostering a deep sense of loyalty. Loyalty programs. Consider a tiered loyalty program that offers exclusive rewards tailored to your most valuable customers. This includes earlier access to new products, personalized discounts, or even point-based reward systems. Personalized experiences. Leverage your data insights to go beyond email. Consider personalized website recommendations, targeted promotions based on past purchase history, or even handwritten thank you notes for high-value customers. Customer feedback loops. Make sure your top customers feel heard. Implement surveys or invite them to participate in exclusive focus groups. This demonstrates you value their input and are actively using feedback to improve the customer experience. Community building. Depending on your business model, fostering a community among your most loyal customers can create a sense of belonging. This could involve access to online forums, exclusive events, or opportunities to network with like-minded individuals. Now, this strategy extends beyond customer satisfaction. Prioritizing the experience of your top customers directly correlates with increased retention, positive referrals, and ultimately improved revenue. Now, let's dive deeper and see who are our most loyal customers.
Alright, so let's now get started with that. Let's create the variable with the name all. So let's first display the first 3 rows of our data frame. So as you can see, there is a row called sales, or the column called sales, and each customer has a specific ID with a specific name. So if you can count up the number of times this shows up, then you also have the number of total orders, which then you can use later however you want to. So let's start with doing that. Now let's rename the columns. We want the column order ID, which is, where is the order ID? Oh, it's right here. We want the order ID to be named total orders. And then we want to rename the columns that are equal to order ID. In this column, this must be renamed to total orders. Place is equal to true. Okay, so now let's identify the repeat customers. Customers with order frequency greater than 1. So repeat customers are equal to customers order frequency, customer order frequency, total orders. And like I said, we want to make sure it's greater than 1. It's equal or greater than 1. Perfect. Now we want to organize this in a way that is descending. We can do that by saying repeat customers sorted are repeat customers that sort values. Perfect. Now let's print this out. Print repeat customers sorted dot add 12. We want to display our top 12 customers. Reset index. So the customer with name William Brown, who is a consumer, has placed total 35 orders. So this is the list of your top how many customers, and as a business or as a superstore, you can identify exactly the number of the total orders a person or a business has to place in order to be considered a loyal customer, and then according to that you can tailor your services to it.
Now the data clearly reveals that a small group of customers place orders with considerably higher frequency, 30 plus. We have William Brown with 35 orders, and other home office customers with 34, and many consumers and one corporate with 32. So this shows clearly that we have loyal group of customers. There's also significant potential for our home office segment. Several of our most loyal customers belong to the home office segment. Now, this implies that the home office segment has strong potential for customers' loyalty and deserves targeted marketing efforts. It also shows that we just don't have one dominant group of loyal customers. We have home offices, consumers, and corporates. While there are many consumers, it doesn't mean that we have to focus on one segment. It means that we still have to devise a plan that caters to our multiple segments. So some recommendations. Now we can prioritize loyal customers. Now segment customers by order frequency, and we can develop exclusive offers, rewards, or early access programs tailored to our most loyal customers. So for example, we can provide them exclusive discounts, tier reward programs, and earlier access. And we can also target more home offices, because we see that home offices keep on coming back, and we are able to satisfy few of the home offices. That means we have catered to their needs and provided a good enough service for them to keep on coming back. That means our product is great for home offices. That means we can target more home offices using content marketing, social media ads, or other type of marketing strategies. And we can also analyze the behavior or the way we provided service to these customers. And because it worked out pretty well, and if we provide this kind of service to our new coming customers, then we increase the chance that they also become a loyal customer. So those are several conclusions we can make. Now we can also identify loyal customers by sales. So this has identified them by total number of orders they have placed, but we can also use amount of sales, so the total amount, to identify them, because a person can come and place 35 orders, but if they place 35 $1 order, then obviously that's just $35. Now this doesn't say anything about the sales amount. So ideally you want to organize it by the sales amount to be able to identify the actual top spending and loyal customers. Or that said, when there is a significant customer, so let's say someone has spent 25,000, that can be done also in one order. So that doesn't mean that it's a repeated customer. It's just a top spender. Now let's start with identifying our top spending customers. So let's first create a variable customer sales equal to data frame that grew by customer ID. We want their customer ID. We want to also see the name and also what type of customer they are, the segment. And we want to do it by sales, and we want to sum those up, and we then want to resend the index. And now let's identify our top spenders by having them ranked descendingly, meaning our top spenders will be ranked all the way up. Customer sales dot sort and values by equal So Sean Miller has spent the most, who is from home office, using total amount of 25,000 USD. William Brown has placed the most number of orders, which are 35, but William Brown is nowhere to be found here. The same as Sean Miller. He's a customer who has spent the most in our Superstore, but he's also nowhere to be found here. Meaning that the repeated customers doesn't really define their spending habits. So depending on the way you run your Superstore, now obviously
I would want our customer to come back, but I would dedicate my resources to the customers who spend the most, because those are the customers who bring the most business to me, meaning those are the customers I have to keep happy. So the total number of orders is great, but it doesn't really speak that much about their spending habits and about their value to your store. Alright, let's now go over to the next chapter, which is shipping. Now, as a superstore, you will also want to know what shipping methods customers prefer and which are the most cost-effective and reliable. And overall, knowing this impacts your customer satisfaction, and also meaning it also has a great impact on your revenue. So, for example, Amazon has multiple shipping methods, but it has the most popular shipping method, which keeps the most amount of customers happy, and it also makes Amazon the most amount of money. So as a superstore, you want to know which one of your shipping methods is the most reliable. So we create the variable type of customers. So our shipping model, let's create a variable. We use the data of the data frame. Ship mode, we want to count those values, and of course we want to reset the index. So our standard class is the most popular it's almost like 4 times more popular. Our first class is the least, and the same day our first class is one of the least. So let's create a pie chart of this. Plotted pie, shipping model. Alright, so this is our class, standard class, or these are like the shipping methods. The most popular one is standard class, which is 60% of the orders use standard class shipping, and rest is like 40%. So as a superstore or as any store, you invest in your shipping. So you end up buying some kind of deals with delivery companies like DHL, UPS, and others. And sometimes you end up recommending the wrong option to your customer. So let's say second class is fast, but it ends up costing the customer way too much. The customer ends up not buying your product, and this decreases as you can see, this hurts your store. But if you know that standard class is the most popular option, then you can have like a button saying this is our most popular option, which is standard class, and most of the time people will choose the most popular option. So this will help the superstore save the cost of investment into these others, or dedicate the amount of resources that each class brings. And it also allows the superstore to recommend its most popular option, which is standard class. So the problem that many superstores have, because many stores have stores in many locations, in many states, but they don't know how well each is performing. On a dashboard, for example, you could have that, but they have no idea how well each of the stores in each state are performing, and leaving them with clueless where there is an underperformance, or for example where there is a high potential area in which they can open a new store in. So let's move on to this chapter, which is geographic analysis. So many stores have hard time in identifying high potential areas or also identifying stores that are underperforming. So things like Walmart, Target, they have like many branches, and they will want to know how well each branch is doing. And the perfect way to do this is by counting up the number of sales for each city, the number of sales for each state, and then this will allow you to see which of the states or which of the cities is performing the best and which of them is performing the least, and dedicate your resources accordingly. So let's say if one city, the store is simply just losing money for years or for more, then you will want to adjust your strategy according to that. So maybe you will want to close the store or adjust it in a way so it starts bringing in more profit or revenue. Well, so let's get started with that. Alright, so as you can see, the most popular state is California and the least popular is New Jersey. So maybe you can go over this, and let's say in a few of the states where there's still high potential for a profitable store, you can identify, let's say in Washington, and calculate. Alright, so maybe from this you can see that Washington is performing fourth, or New Jersey is performing like the least of our top 20. From this you can conclude that you might have to work on New Jersey more to increase the order count. This also allows you to increase the revenue. Or you can see that the California is your most popular option, so you might want to keep California happy. And you can also do it per city. So city TF, city value counts, reset, next, print city.head, the most top 15. So the most popular city is New York with the order count of 891, and then Los Angeles, and Jackson is the least popular out of our top 15, and you can also increase this to 25. So not only can you focus on the states, but for each state you can also focus on the city that's underperforming or overperforming. So this allows you to also dedicate your resources to the city that you want, maybe to increase your revenue or increase your potential. Or maybe there is like a city, for example Long Beach, where there's high potential but you are not using any of your resources. Now we can also organize it sales per state. Let's say state sales. So previously we did it by order count, and we can also do it for state sales. We want to sum it up and then reset the index. We want to rank it according to perfect. So as you can see, our most popular state is California, and then New York, and then it changes it, and then it doesn't change yet, Texas. So this is according to the sales amount, the popularity of the state according to the sales amount. And let's also sort it for per city. So most populous city is New York, LA, Seattle, San Francisco. So this is exactly the same as our previous analysis around the city. Nothing really has changed. Alright, so as a store, you want to be able to track down your most popular category of products, or your best-selling products, or sales performance across categories and subcategories, and find the sweet spots where strong categories also have top-selling subcategories, and also spot weaker subcategories within otherwise strong categories that might need improvement, or product popularity fluctuations. See if popularity is seasonal, turning up and down, and this helps to forecast the future demand. Or you can group it by location. For each location, there might be a different popular product. You want to put it in a certain place to maximize your store's revenue. So let's get started with finding our top performing products or their categories. So let's first extract our products, the categories of our products from our data frame, that unique print products. So right now in our data frame, we have only 3 sorts of products. As you can see, the category, and each one has a subcategory, bookcases, chairs. But we have mainly 3 categories, which are furniture, office supplies, and technology. So let's go now over to the types of subcategory. Our product subcategory, the unique print product subcategory, bookcases, chairs, tables, and bunch of it. Now, let's group the data by a product category and how many subcategory it has. So we want to say, for example, office supplies may have like 20 subcategories, or furniture may have 5 subcategories. So let's see how many subcategories each one has. So there are nine for office supplies, 4 for furniture, 4 for technology. So office supplies is much more sophisticated category. Now we can also see our top performing subcategory. So let's say a subcategory, and then you want to count the sales. We'll go by category. So our most popular subcategory is tech, specifically phones. It has the most amount of sales, furniture, chairs, office supplies, storage. So from this you can see our most popular subcategories and what subcategories you want to recommend them on a front page or in the store. Now let's see which one of our main categories performs or has the most amount of sales. Product category, go by. So as expected, tech is the most popular one, and then furniture, and then office supplies. So maybe you will have inside your store, you will have a much larger department, or not much larger, maybe a little bit larger, or maybe it's in the first row, right in front of the customers, to be able to present your most popular option immediately to your customers. Now this will allow you to, of course, increase your revenue and sales. If you want to create a pie chart for this, you can say product pie, top product category. You can organize it by sales, labels, top product category. And there's already, well, it seems that tech is performing a little bit better than most, or like these two, but it's not that much different. It's not really that different. Alright, so let's now see which one of our subcategories is the most popular one. Now remember that we saw which one of our subcategories had the most amount of sales. Now let's create a bar graph out of it. We can do this by ascending false, insert the value by sales, ascending is true. Let's create the bar graph out of it. Solid bar, subcategory count sales is subcategory, top product subcategory. This is sales. Let's pull it. And summary is going to be fine. Now this shows perfectly that our most popular option is phone and chairs, and so since these generate the most amount of sales, that means that customers are more willing to pay money for this. So you can end up spending more of your marketing resources on phones and chairs, because there is already shown that because of the amount of resources you have provided for phones and chairs, it already works. Meaning if you increase the amount of resources you spend for phones and chairs, then your sales will also increase accordingly. But you can also conclude that art, envelopes and labels aren't that popular. So maybe right now you can give a discount and get rid of those and buy less of those for the future. So you can end up buying more of the popular options, for example, phones, chairs. Or you can also investigate why they are not popular. Maybe those are like the worst envelopes you could have bought, or maybe it's not the right art you have bought. Maybe those kind of art people don't like, but if you were to choose complete other form of art, maybe customers will end up buying them. So this shows exactly how this data stores can use to optimize the sales or optimize how their resources are allocated, so you would end up making more money or more sales. Now, businesses love making sales. They love seeing revenue increase and profits increase. That's all lovely, but you should be able to track down your sales so that you can see in what kind of situation you are, and you can adjust to that situation. And what is a better way than having a pie chart or a bar graph or just a normal graph to see how much growth or how much decline you're experiencing. For example, if you are a business and there's a declining revenue, then year over year or month over month, then you can see that there is a problem. And then you can also allocate your resources towards fixing that problem, whether that is investing more in customer preferences or investing more money into marketing or into resources that make your customers more satisfied, or adapting new technologies. Those are all things that you can do whenever you see a declining revenue, but first you must be able to see it coming. And also businesses have a problem with stagnant growth. So they may grow 1 month and the next month there's like no growth, or maybe there's a decline. So you want to see that as a business to be able to stabilize the growth, so continuously grow as a business. Or missed seasonal opportunities. If a business isn't aware of how sales changes throughout the year, they could miss out on maximizing profits during peak seasons. Maybe on some seasons there's a certain product that's high in demand, but you don't have enough stock to cover it, so you end up not being able to meet the demand and losing out on revenue and profits. And those were regarding our yearly sales trends. And there's also a problem with quarterly and monthly sales. So for example, cash flow issues. Now many businesses experience cash flow issues, so that maybe one day they look at their bank and see that they are out of money and they cannot invest more in their business. Or there's also inventory imbalance or ineffective marketing. So for example, whenever you have a cash flow issue, drastic dips in sales during specific quarters or months can lead to cash crunches, making it hard to pay suppliers, employees, or ongoing expenses. Or whenever you have inventory imbalance, some periods you're overstocked and those items you have to give away, and some periods you're understocked and you are not able to meet the demand. Or maybe your marketing is ineffective. So if you spend significant amount of time in marketing and you don't reach your desired outcome, that means there's a major issue with your marketing campaign. And then you can see that from the sales you're making. So for example, if you're spending this amount of money with marketing or increased amount of marketing and there's no significant increase of sales, that means you're doing something wrong with your marketing campaign. Or lagging in response to emerging trends. So monthly sales data can highlight new trends or drops in demand more quickly than just yearly overviews. So you can react much faster to emerging trends. For example, a certain product was released 2024 and all of a sudden it's high in demand in many countries. Then you want to be able to adjust to that demand and get the supplies for the product. But you are not able to do that if you track yearly sales or don't do any tracking at all. So those are all the problems that exist if you are not able to track down your sales, be it monthly, quarterly, or yearly. And so we are intending to solve that problem by graphing it and concluding from the results we get from our graphs. Alright, so let's get started. Now let's convert the order date column to a data frame format. The order date is equal to pd.to datetime df. Order date, day first, is equal to true. Now let's group the data by years and calculate the total sales amount for each year. We can do it by yearly sales, creating the variable first, and then group by df order date dot year sales dot sum yearly sales is equal to yearly sales. Let's reset the index. Now we want to give the appropriate colors the appropriate name, because right now in the data frame it's not. The order date should be named year, and sales should be named total sales. Now let's print this out. So this is the amount of sales for each year in total, and we can also, let's plot the bar graph out of this. Plot that bar, yearly sales, year, yearly sales, total sales. Alright, so from this bar graph, there can be a few conclusions made. For example, there's a steady growth from 2016 to 2018 that might explain, for example, new product launches, that they are effective, or economic factors, or marketing efforts. Those are all the explanations that a person can make, but you can make these conclusions only when you have a larger data available to you. And in this data frame, we don't have the marketing costs or any other costs involved regarding this. So that's, our conclusions are pretty limited, but what we can see is that this bar graph combined with any other bar graph, for example, marketing costs, you can make a pretty good amount of conclusions from that as a business. Now, how about totals? We can also plot this using just a normal graph, which means I will just copy it, or no, I won't. Just plot it, yearly sales, year, total sales. So this shows a little bit different. Now, I prefer this sort of graph for, instead of a bar graph, for tracking the yearly sales, because it shows much more clearer the amount of increase with the amount of decrease. We can also focus on the quarterly sales, like I said, to be able to react to emerging trends, or to react fast to, or to be able to react fast to any kind of change. Now let's again convert the order date to a date format, order date. From our quarterly sales, we can see that there is a steady increase of quarterly sales, and all of a sudden, July it blows up to new heights. So from this graph, we can see exactly that Q3 and Q4 did very well, and Q1 and Q2 didn't. So something might have changed. For example, a seasonal trend, or you have increased your marketing, or you have introduced a new product, or you have targeted a specific customer segment. And as a business, it's really important to know that. So you can also expect that if you follow a similar line of actions, then you might have higher demand for your products on Q3 and Q4. So you might want to overstock it. Or maybe you can analyze this further and replicate these successful strategies for future quarters. And this will make sure that a business can steadily grow and increase its revenue, which is good. And also for Q1, you can see that it starts out with pretty slow. I mean, businesses may want to start out the year more quickly, so they can investigate it also. For example, is this a seasonal for the industry? Maybe on certain seasons, a certain product is not high in demand, or maybe a competitor did some kind of a marketing or use some kind of a strategy to drive more customers to them. Or maybe we have changed marketing effort in our Q3, and our marketing efforts were not productive for Q1 and Q2. So maybe that's it. Alright, so maybe you want to investigate this much more deeply, so not quarterly, but monthly. So let's do that now. Let's start off the same way. Call the order date column to the data time format. DF, order date, periods to daytime. Alright, so from this graph you can see that it's growing month over month, beside first month of 2019 and also the third month of 2018. So this is generally an upward trend, which might suggest like a healthy sales going on. And it looks like August and December might be your seasonal, so you might want to overstock the products there. And okay, you can also see that there are seasonal dips in third month of 2018 and also 2019 in November of 2018. So you might want to consider like seasonal promotions to stimulate off-season sales, or diversify your product service offerings to reduce the reliance on seasonal demand. Or maybe you want to start deploying new marketing strategies here, or try to target new customer segments by introducing new products so that you might offset the seasonal trends. And overall it seems pretty consistent. So it looks like that there's a healthy sales trend, so you might want to invest more in your proven strategies, which might be, for example, a certain marketing tactic, promotion, or product offering for a certain month. And like I said, for the dips, the store might try to deploy new marketing strategies or introduce new products to target new customer segments, which might offset the dip. And that said, it's important to consider the longer time frame. A year certainly has great amount of data, but it does not really accurately reveal seasonal patterns, because for 1 year that might be the case, but for another year it might just be completely the opposite. So you might want to consider a larger sales line graph, for example, maybe for 5 years, and then you can see if that's the case. And if that's the case, then this might suggest a seasonal trend. And if not, then you will act accordingly. Alright, so we have covered the sales trends. We can move on to the next chapter, which is... Alright, let's move on to the next chapter, which is mapping. So we want to create a map out of sales per state. So for each state, we want to color it according to the amount of sales. So if there is a high amount of sales, then it should be colored yellow. And if there is low amount of sales, then it should be colored blue. So the question is, why would someone want to do this? Now, companies looking to expand into new geographic areas face the challenge of identifying the most promising states and regions for their products or services. Now, for example, how do you know if your product will sell in a certain state? So one of the tactics that people often use is by seeing if there is a similar store like them operating in that state or in that city. And so if there is a similar store working there, and it's not a saturated market, meaning there are still plenty of amount of people who might buy your product, then it's a good idea to go there. For example, a company that manufactures athletic apparel is considering expanding its retail footprint. By analyzing total sales data by US state, they can see that states with a high concentration of fitness centers and active populations, like for example California, Texas, or Florida, might be good candidates for new stores. And if there are currently no sports stores there, then it's even better. Or for example, if you're a business and you want to strategically allocate your market budget and sales team, and so you have stores all over the states, you want to optimize it for each state. Maybe one state is performing well and another state is not performing. So you might then, from the map, you might see which state is not performing well and allocate your resources accordingly to be able to maximize your return on investment by optimizing certain strategies. But if you don't know which state is not performing well, then if you don't know which state is performing well, then you have no information on where you have to optimize. Like for example, a national pizza chain wants to optimize its marketing spend. Now, sales data reveals that their pizzerias in the Midwest consistently outperform those on the West Coast. Now, this data suggests that they might need to allocate more marketing budget to increase brand awareness and sales in the Western states. And you might also want to do this because of competitor analysis. So staying ahead of the competition means understanding where your competitors are having the most success. Analyzing their sales patterns across states can reveal their geographic strengths and weaknesses. Now, for example, a coffee roasting company notices a competitor coffee brand is experiencing high sales in the Pacific Northwest states. Now, this could indicate the competitor has established a strong partnership with local grocery stores or launched successful marketing campaigns in that region. Now, the company can use this information to target similar grocery stores or develop competitive marketing strategies for the Pacific Northwest. So without further ado, let's get started with it. Now, I will walk you through the code, and instead of writing it, I will just walk you through it. So let's first import the plotly graph function or the library. So we initialize the plotly in our Jupyter notebook, and we also want to create a map for all 50 states, which we do this right here, and add the abbreviation column to the data frame, because right now there is not. We initialize the variable and calculate the amount of sales for each state and group it by state. And this is exactly what we need. And then we add the abbreviation to sum of sales. We do that here. And finally we plot it. And this is how the map looks like. So the blue area are the ones with low amount of sales, and the yellow area, which is California, has high amount of sales. So from this map you can see which areas main sales come from, and according to it you can optimize accordingly. So let's say you have a pizza chain or a pizza chain of stores, and you want to see which one of your states is performing the best and which one is performing the poorest. So you want to spend your most energy on optimizing what doesn't work. So from this you can see California is great, so you can leave it alone. But for example, Texas is not performing that well. So you might allocate more marketing budget or more resources there to start making or to start getting more sales, because in Texas there are still many amount of people who consume pizzerias, but they are not buying. So why is that? And you can also see, so for example, if this is a completely another store, this is like relates to, for example, a retail store for sport goods, and all of these states, they've got a store in. Now from this you can conclude that California is performing real well. So it's probably not a good idea to go there, since there might be a market saturation there. But you can go, for example, Florida. You might go to Florida and start selling similar sport goods there, because like you see, the market is still new, or the market is still not saturated. Alright, so that was that. So we can also create a bar graph out of it. Now from this you can see that most of the total sales by state, California is doing the best, and North Dakota is doing the worst. And of course, now as you remember, we previously categorized or showed how large each of our categories are, and we did the same for our subcategories, but we never did it in the same plot. So here we display our main category of products, which are furniture, office supplies, and technology. And for each category we have subcategories, and based on their size, it's organized based on their size. So chairs, it seems that chairs is the largest or sells the most in our furniture category. Then it goes to tables, and we have then a small amount of bookcases and furnishings. And in our office supplies, you can see that the best storage product is performing the best. and envelopes and labels are performing the worst. And for our tech category, phones are performing the best, and then machines, accessories, and copies. And from this you can see that phones is overall the best subcategory. I think it's even larger than chairs. Yeah, a little bit larger. So this is a much better way to display if you're trying to make an argument, to display the plot. And of course you can also do it this way. Alright, and hope you guys enjoyed this project. I definitely did, and I will see you guys in the next video.
This video was sponsored by one data point at a time.